to Sleepy Facts with Justin. Tonight, we are going somewhere very far away. And yet, we are going home. We are going to explore the Milky Way galaxy. The galaxy you already live inside of. The great spiral of stars and dust and quiet darkness that has been slowly, gently turning for over 13 billion years. There is no need to go anywhere. You can stay exactly where you are. You can be warm and still and comfortable. Let your body sink a little deeper. Let your shoulders soften. Let your breath come slowly. Because the Milky Way is not going anywhere either. It has been here since nearly the beginning of time itself. It will still be here long after tonight is over. And so, there is no rush. No rush at all. The Milky Way is a barred spiral galaxy. Those words may sound large and complicated, but the shape is actually quite beautiful and quite simple. Imagine a slow, graceful pinwheel, long curving arms made of hundreds of billions of stars, all turning together, all held in place by gravity's invisible, patient hand. From edge to edge, the Milky Way stretches roughly 100,000 light years across. That is a distance so vast, so gently incomprehensible, that the only right response is simply to breathe, to be still, to let the mind soften around a number that was never meant to be fully held. Our own sun, the warm star at the center of our solar system, lives about halfway out along one of those spiral arms. Not at the center, not at the edge, somewhere quiet in between. A calm, unhurried neighborhood of the galaxy. A place where, for billions of years, the conditions have been just right for life to take root and grow slowly, like a flower opening toward light. The galaxy holds somewhere between 200 and 400 billion stars, each one a sun, many of them with their own planets turning around them in slow and faithful orbits, and all of them, every single one, part of the same great turning family. Tonight, across the next several hours, we will drift through this family together. We will visit the ancient spiral arms, glowing with the blue blue light of newborn stars, we will pass through clouds of dust and gas so vast that a single cloud would take millions of years to cross. We will float near the quiet, sleeping heart of the galaxy, where a black hole 4 million times the mass of our sun rests in stillness. We will meet the oldest stars, the ones that formed before Earth existed, drifting slowly in the deep surrounding dark. And through all of it, you need only rest. Let the words wash over you like a slow tide. If your attention drifts, that is perfectly all right. That is exactly what this journey is for. You are here. You are safe. And somewhere above you, though you cannot see it from where you lie, the Milky Way is turning. Slowly, quietly, the way it always has. Let us begin. Here is section 1 of Sleepy Facts with Justin. The Milky Way galaxy, written at approximately 1,500 words for 30-35 minutes at AF Nicole 0.7 speed. Section 1. A river of light, how ancient peoples saw the Milky Way long before there were cities, long before there were electric lights, or glowing screens, or the warm hum of modern life. Human beings lay on their backs in the dark and looked up, and what they saw above them was something that we, in our bright and busy world, rarely see anymore. They saw the Milky Way in its full and quiet glory, a soft, pale band of light stretching from one horizon to the other, a river of stars so dense, so gently luminous, that it seemed to breathe. Imagine lying in cool grass, the earth solid beneath you, the night air soft and still, and above you that slow river of light threading its way across the whole sky. Not harsh, not blinding, just a soft, silver glow, the kind of light that asks nothing of you, the kind of light that simply is. For our earliest ancestors, this was the sky every clear night. And because human beings have always needed to make meaning of the beautiful things they cannot explain, every culture on Earth looked up at that band of light and told a story about it. The stories are as different as the people who told them, And yet, in some quiet way, they all carry the same feeling, a sense of wonder, a sense of connection, a sense that the sky was not empty, but full of something vast and ancient and alive. Let us travel through some of those stories now. Let them wash over you slowly. There is no need to remember them, no test to pass. Just let them drift through your mind like the light they were trying to describe. We begin in ancient Greece, because it is the Greeks who gave us the word we still use today. The Greeks called that pale band of sky galaxies Kyklos, the Milky Circle. The word galaxies came from their word for milk, gala. And from that single Greek word, spoken thousands of years ago, we eventually got our modern word, galaxy. Every galaxy in the entire universe carries a name that traces back to an old Greek story about a sleeping goddess and a baby. The story goes like this. Zeus, the king of the gods, had a son named Heracles, born of a mortal woman. Zeus wanted his son to become immortal, and for that, the infant needed to drink the divine milk of the goddess Hera. But Hera was not the boy's mother, and she was not pleased. So Zeus waited until Hera was asleep and brought the infant quietly to her side. Heracles, already extraordinarily strong, latched on too forcefully. Hera woke with a start, and in the struggle, her milk sprayed upward across the whole of the night sky. And there it remained, a long, pale arc of light, the Milky Way. It is a vivid story, and perhaps what is most remarkable about it is not the story itself, but what it tells us. It tells us that even in ancient Greece, people looked at that band of sky and felt it needed explaining, felt that something so beautiful must have a cause, must have a story behind it, must have been placed there intentionally by forces larger than themselves. The Romans carried the Greek story forward, as they often did. They translated the Greek galaxies into Latin and called it the Via Lactea, the Milky Road, and they saw it not only as spilled milk, but as a road, a great celestial highway along which the gods themselves traveled, a path from the mortal world to the divine. Now let us drift further east to ancient Egypt. For the Egyptians, the night sky was not an empty space above them. It was a living being. The sky was the body of the goddess Nut, who arched herself over the earth, her fingers touching one horizon and her toes touching the other. Her body, stretched across the dark, was studded with stars. Researchers studying ancient Egyptian texts and astronomical simulations now believe that the pale band of the Milky Way was connected to Nut herself, that the soft glow running along her outstretched body was understood as part of her divine form, a celestial figure so large that her body contained all of the stars, all of the light, all of the night. Each evening, the sun god Ra was swallowed by Nut as the sun set in the west. And each morning, she gave birth to him again as the sun rose in the east. The sky was not still. It was not empty. It breathed and swallowed and renewed. Let us move now. Let us drift quietly northward to the cold, dark winters of ancient Armenia. In Armenia, the Milky Way was called Hord Gagai Chanapar, the straw thief's way. The story tells of a god named Vahan who stole a great cartload of straw from the Assyrian king Barsham during a bitter winter. Vahan needed the straw to warm Armenia through the cold. He fled across the heavens with his stolen cargo. And as he ran, wisps of straw fell from the cart and drifted across the sky. The pale, scattered light you see on a clear night, that is the straw that fell. It is a gentle kind of story. A god running through the dark, clutching something ordinary and useful, dropping pieces of warmth along the way. There is something very human in it, very tender. Now let us visit Finland and the soft, bird-like imagery of the north. In Finnish, the Milky Way is called Linnanrata, the pathway of the birds. The ancient Finns observed that migratory birds, geese and swans and cranes, seemed to follow the band of the Milky Way as they flew south for the winter. The pale streak of sky was their road, their guide, and at the end of that road, far beyond the southern horizon, was a warm and distant place the Finns called Lintukodo, the home of the birds, a place of gentle warmth where the birds vanished each autumn and rested until spring. Imagine watching a great flock of birds in the autumn evening sky, their wings catching the last of the light, following that pale celestial road south. It is a quiet, unhurried image, the kind of thing you could watch for a very long time. Far to the south, the San people of southern Africa had their own way of seeing the Milky Way, and their story is perhaps the most touching of all. Long ago, according to the San, there were no stars. The night was completely dark. A young girl, lonely in the darkness and wanting to find her way to other people, scooped up the glowing embers from her fire and threw them up into the sky. They scattered and stuck and became the stars. The Milky Way, that dense sweep of light, was where most of the embers fell. She threw her fire into the dark so she would not be alone, and it has been there ever since. A road of light made from a single act of longing. Across the Pacific, the Navajo people of North America told a different kind of story. When the world was new, the holy people gathered carefully around the fire god, choosing stars one by one from a sacred bag and placing them gently in the sky, each in its proper position, each with its proper name and meaning. But the trickster coyote grew impatient with how long this was taking, and in a burst of mischief, he grabbed the bag and threw all the remaining stars up into the sky at once. They scattered widely and landed where they fell, in no particular order, with no particular names. And that great, unnamed scatter of light became the Milky Way. The stars of the Milky Way in Navajo tradition cannot be named because they were not placed with intention. They are the beautiful consequence of impatience, of a trickster's restless energy frozen into light. And so it goes across every culture, on every continent, beneath every clear night sky. People looked up at that gentle band of light and felt compelled to reach toward it with their stories, to make it theirs, to weave it into the fabric of meaning that held their world together. The names alone are like a soft catalog of human wonder. The pathway of the birds, the straw thief's way, the way of the white cow, as the ancient Irish called it, the road of ashes, the divine way, Odin's way, the silver river, as it is still called today across much of China and East Asia. All of them the same band of light. All of them the same river of stars, seen from different shores in different seasons by different people who all felt in some wordless way that what they were looking at was something important, something worth remembering, something worth passing down. And they were right. That river of light above them was their home. It was all of our homes. It still is. And tonight, over the hours ahead, we are going to explore it together, slowly and gently, from the inside out. For now, just breathe. Let the old stories settle around you like starlight. Let your body be heavy and still. You are warm, you are safe, and above you the river of light turns on. There is something deeply restful about a spiral. Think of a spiral for a moment. Think of the slow curl of a nautilus shell, the soft, widening rings on the surface of still water after a raindrop falls, the gentle coil of a fern unfolding in spring. Spirals appear everywhere in the natural world, in places where growth and time and motion have shaped something beautiful without any plan, without any effort. The Milky Way is a spiral. A great, slow, turning spiral of stars and gas and dust, shaped over billions of years by nothing more than gravity and time. And though it is almost impossibly vast, its basic form is something we can hold gently in the mind, something we can picture quietly as we rest. Let us spend this time doing just that. Let us trace the shape of our home slowly from the outside in. If you could somehow leave the Earth and travel outward, not in a hurry, not with any urgency, just drifting gently farther and farther from the sun, past the outer planets and into the cold dark between the stars. And if you kept drifting for an unimaginably long time, until you were so far away that the entire Milky Way lay below you, what you would see from that great distance would be something like this: a flat, luminous disk, softly glowing, turning with extraordinary slowness in the dark. From above, it would look like a pinwheel, like something a child might hold up into the wind on a summer afternoon, its arms curved and reaching, rotating in a single grand direction. From the side, the same disk would look different. It would look like two plates pressed gently together face to face, thin at the edges, thicker and brighter toward the middle, where a soft bulge of ancient stars would glow with a warm amber light, not the bright blue-white of young stars, but the deep, settled gold of stars that have been burning for a very long time. This is the shape of our galaxy, a disk with a bulge at the center, and winding through the disk like the arms of that slow pinwheel, the spiral arms. The numbers attached to this shape are large, but let us sit with them quietly rather than being dazzled by them. The disk of the Milky Way stretches approximately 100,000 light years across. 1 light year is the distance that light travels in a single year, and light moves faster than anything else in the universe. In 1 second, light travels nearly 300,000 kilometers. In 1 year, it covers almost 10 trillion kilometers. And across the full width of our galaxy, that light would need to travel for 100,000 years. Let that rest in your mind without trying to fully understand it. It is too large for full understanding. It is the kind of number that is meant to be felt rather than grasped, like holding your hand up to the sky and knowing, not quite seeing, that behind the blue there is an infinity of space. The disk is wide, but it is also surprisingly thin. compared to its diameter, the disk of the Milky Way is extraordinarily flat. The spiral arms, where our own sun lives, are only about 1,000 light years thick. The galaxy is, in proportion, far thinner than a sheet of paper would be if that sheet were scaled to the same width. A flat, thin, turning disk, glowing softly in the dark. Within that disk, there are two distinct layers. Scientists call them the thin disk and the thick disk. The thin disk is where most of the activity happens. It is where the spiral arms are, where the bright young stars live, where gas and dust drift in great soft clouds, slowly collapsing under their own gravity to form new stars. The thin disk is alive with change, though that change unfolds over millions of years. By human standards, it is still and calm. The thick disk is older, quieter. It sits above and below the thin disk like a gentle, faded glow. The stars in the thick disk are ancient, most of them more than 10 billion years old. They formed in the galaxy's early youth, when the universe was young and dense, and the first great waves of star formation swept through the cosmos. Those stars have been burning quietly, steadily, for an almost unimaginable span of time. They contain far less of the heavier elements, the carbon and iron and oxygen that later generations of stars would produce and scatter. They are simpler stars, old stars, stars that have seen more of the universe's history than almost anything else we know of. At the center of the disk, rising from its middle like a soft glow at the heart of a lantern, is the galactic bulge. The bulge is a rounded, roughly spherical region of older stars, packed more tightly together than the stars in the outer disk. It stretches about 10,000 light years across, and it shines with that warm, amber light of ancient suns. And running through the center of the bulge, like a slow axle through the turning wheel, is the galactic bar. A long, dense concentration of stars arranged in a straight line through the heart of the galaxy. This bar stretches for roughly 27,000 light years from end to end. It was the presence of this bar that led scientists to classify the Milky Way as a barred spiral galaxy. Not simply a spiral, but a barred spiral. The bar was confirmed by the Spitzer Space Telescope in 2005, when infrared observations finally pierced through the dust and gas that obscures the galactic center and revealed its true shape more clearly. The bar turns slowly, like a slow hand on a cosmic clock, and at each end of the bar, the four great spiral arms begin their long, curving journeys outward through the disk. The spiral arms, the four great arms of the Milky Way, have names. The Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm. They wind outward from the ends of the central bar, curving gently through the disk, each one a dense river of stars and gas and dust. Between these major arms, there are smaller structures, spurs and bridges, and shorter arcs of stars, connecting the great arms like quiet country roads between major highways. Our own solar system sits in one of these smaller structures, a spur called the Orion Arm, or the local arm. We are not in one of the great spiral arms themselves. We live in a quieter, more modest region, a spur, an offshoot, a gentle side street of the galaxy. The spiral arms are not solid structures in the way that, say, the spokes of a wheel are solid. They are regions of greater density, places where stars and gas crowd together a little more than in the spaces between the arms, like a slow wave moving through a crowd. The density wave passes through the disk, and as it does, it compresses the gas it encounters, triggering the birth of new stars. The bright, blue-white stars that trace the spiral arms are young. They formed recently, drawn into being by the compression of the passing density wave. They burn brilliantly and briefly, living only a few million years before burning out. And because they are so short-lived, they are always found near where they formed, always near the arms. They are the galaxy's way of drawing its own shape in living light. And then, beyond the disk, beyond even the thin scattering of stars at the disk's outer edge, there is the halo. The halo is not a bright structure. It is vast and nearly empty. A great, roughly spherical region surrounding the entire disk, extending far out into the dark. Within the halo float the globular clusters, ancient spherical swarms of stars that orbit the galaxy like slow, faithful satellites. There are about 150 of them, scattered above and below the disk, following long, looping paths around the galactic center. And beyond even the halo, extending further still, is the dark matter halo, a region of matter that cannot be seen, that emits no light and absorbs no light, but whose gravity shapes everything within it. We will return to dark matter later in our journey. For now, let it simply be a reminder that most of what our galaxy is made of cannot be seen at all. So this is the shape of our home. A thin, flat disk turning slowly in the dark. A warm central bulge of ancient stars. A long bar through the heart. 4 great spiral arms winding outward, alive with young stars and drifting clouds of gas. A surrounding halo of old star clusters. And beyond all of that, the invisible embrace of dark matter, holding it all together. It is a structure of extraordinary elegance, not designed, not planned, but shaped slowly over billions of years by nothing more than the patient, persistent pull of gravity. Gravity does not rush. It does not force. It simply draws things together, gradually, tenderly, over timescales so vast that the result is always something beautiful. A spiral, a pinwheel, a river of light. It's our home. Let your body rest now. Let the shape of the galaxy settle in your mind like something soft and familiar. You live inside a spiral. You always have. And as you rest here, in the dark and the quiet, that spiral is turning above you slowly, as it has for billions of years. There is nothing you need to do, nowhere you need to be. Just rest and let the great slow turning carry on without you. of all the things we will explore on this long, gentle journey through the Milky Way, perhaps none is more quietly remarkable than this. We are not outside the galaxy looking in. We are inside it. Every star you have ever seen in the night sky is a member of the same galaxy as our sun. Every constellation, every shooting star, every soft glow you have ever noticed on a clear night far from the city, all of it is the Milky Way, seen from the inside. We are not observers of the galaxy. We are inhabitants of it. And the place where we live within this vast spiral is a place of particular quiet and particular grace. Let us spend this time simply being here, noticing where we are, letting the neighborhood sink in slowly. Our sun sits approximately 26,000 light years from the center of the Milky Way. Not at the center, not at the edge, roughly halfway between the two. It is a middle position in every sense of the word, a moderate, temperate, unhurried location in a galaxy that spans 100,000 light years from end to end. Think of it this way. If the entire Milky Way were the size of the continental United States, our sun would be somewhere around Kansas. Not the bright heart of things, not the distant frontier, just a quiet place in the middle where the land is flat and open and the sky is wide. And just as Kansas sits between coasts, between mountain ranges, in a kind of calm geographic middle, our sun sits between the great spiral arms of the galaxy, not inside one of the main arms, where stars crowd together and massive suns burn hot and briefly before exploding, but in a quieter region, a smaller structure called the Orion Arm, or the local arm, a spur, a side branch of the great Perseus Arm, stretching some 20,000 light years in length and roughly 3,500 light years wide. It is a modest address, and it turns out that a modest address may be exactly the right one for a star that wants to nurture life. Astronomers have a concept called the galactic habitable zone. Just as planets have habitable zones around their stars, regions where liquid water can exist on a surface, and where conditions for life are possible. Galaxies, too, may have habitable zones, regions within a galaxy where the conditions are just right, not too close to the violent, radiation-drenched center, not too far out in the sparse outer regions where the heavier elements necessary for building planets and living things are rare. Our sun sits comfortably within this galactic habitable zone, far enough from the center to avoid the intense radiation and gravitational chaos that reigns near the supermassive black hole at the galaxy's heart. Close enough to the center that the gas from which our solar system formed was rich in the heavy elements forged in earlier generations of stars: iron, carbon, oxygen, calcium, the ingredients of rocks and oceans and bones. It is a balance, a careful, accidental balance, arrived at by nothing more than the slow sorting of gravity and time. And yet, the result is a star in exactly the right place, with exactly the right ingredients, at exactly the right moment in the galaxy's long history. There is another reason our location is fortunate, and it has to do with the spiral arms. The spiral arms of the Milky Way are beautiful, but they are also dangerous. They are dense with massive, short-lived stars that burn brightly and violently, and then explode as supernovae. These explosions release enormous amounts of radiation. They send shock waves through the surrounding gas. They are transformative events. And for a planet trying to quietly nurture life over billions of years, frequent close encounters with supernovae would not be helpful. Our sun, in its position between the major arms, crosses through a spiral arm only rarely. And there is something even more remarkable about this. Our sun orbits the center of the galaxy at very nearly the same speed as the spiral arm pattern itself rotates. The arms rotate as a wave, and the sun moves at almost exactly the same pace. This means that our solar system stays, for long stretches of time, in the quiet space between the arms, avoiding the chaos, drifting through a calmer region of the disk. This synchronization was not planned. It was not arranged. It simply emerged from the particular values of our sun's orbit. And yet, it has given the Earth billions of years of relative quiet in which life could slowly, patiently develop. Now let us look at the neighborhood more closely. The immediate surroundings of our sun on a galactic scale. Our sun lives within a region astronomers call the local bubble. The local bubble is a cavity in the interstellar medium, a region of gas and dust that fills the space between stars. Most of the galaxy's disk is filled with this interstellar medium, sometimes denser, sometimes thinner, drifting in great slow clouds. But the local bubble is a region that has been swept relatively clear. It stretches roughly 1,000 light years across, a vast but gossamer emptiness in the fabric of the galaxy. Astronomers believe the local bubble was carved out by a series of supernovae that occurred millions of years ago. Those ancient explosions drove the surrounding gas outward, leaving behind a region of unusually thin, hot, rarefied gas. Our sun has been drifting through this bubble for millions of years. Within the local bubble, our sun drifts through an even smaller region called the local fluff. A warm, slightly denser cloud of gas, about 30 light years across, through which our solar system is currently passing. The local fluff is made mostly of hydrogen and helium, with traces of other elements. It is extremely thin by earthly standards, more empty than the best vacuum ever produced in a laboratory. And yet, it is not nothing. It is the immediate medium through which our solar system moves as it travels through the galaxy. And move it does. Our entire solar system, the sun, and all its planets and moons and comets and asteroids, is traveling through the galaxy at approximately 828,000 kilometers per hour. That is a speed that is almost impossible to feel or imagine from where we stand. And yet, even at that extraordinary speed, it takes our solar system approximately 230 million years to complete one full orbit around the galactic center. One orbit, one galactic year, 230 million of our years. In the entire history of the Earth, our planet has completed only about 20 of these great galactic orbits. The last time we were in the same position in the galaxy that we occupy today, the first dinosaurs had only just appeared on Earth. Mammals did not yet exist. The continents looked different. The oceans sat in different places. And still, in cosmic terms, 20 orbits is not a very large number. The Milky Way itself has completed perhaps 50 or 60 such rotations since it first formed. Our nearest stellar neighbor, the star system called Alpha Centauri, lies about 4.25 light years away. 4.25 light years. In human terms, an inconceivable distance. The fastest spacecraft ever launched by humanity would take tens of thousands of years to reach it, and yet in galactic terms, Alpha Centauri is practically next door. A neighbor close enough to wave to, on the scale of the Milky Way. Within about 17 light years of our sun, there are roughly 50 known star systems. Some are single stars like our sun. Some are pairs, binary systems, where two stars orbit each other in a slow gravitational waltz. Some are dim, small, and cool, red dwarf stars that burn for trillions of years on modest reserves of fuel. Some are white, hot, and young, each one a sun, each one a potential center of its own small family of worlds. This is our neighborhood. 50 star systems in a volume 17 light years across, scattered in the dark like lanterns in a very large and very quiet forest. There is something profoundly reassuring about this image. We are not alone in the galaxy, in the simple sense that the galaxy is full of stars, full of suns, full of worlds we have not yet seen and cannot yet reach. And our sun, in its quiet middle position, in its gentle spur of a spiral arm, in its swept clean bubble of interstellar space, is simply one of these, one lantern among hundreds of billions. Neither special nor insignificant, just here, quietly here, doing what stars do, burning steadily and warmly, holding its small family of planets in a careful and patient embrace. And on one of those planets, very small and very blue, life learned to look up, learned to ask where it was, learned slowly, painstakingly, beautifully, to understand at least something of the answer. You are here, in a quiet arm of a great spiral galaxy, in a local bubble swept clean by ancient stars, on a planet orbiting an ordinary sun, traveling at 800,000 kilometers per hour through the dark. And right now, you are resting, still and warm, while all of that motion, all of that vast and silent movement carries you gently along. There is nothing to do, nothing to worry about. Just rest and let the galaxy carry you. If you have ever watched a slow river from above, you may have noticed how it curves. A river does not travel in a straight line. It wanders. It bends. It finds the path of least resistance through the landscape, carving wide, gentle curves across plains and valleys, and seen from a great height, a river looks almost like something alive, like it is reaching, like it is searching. The spiral arms of the Milky Way have something of that quality. They are not straight. They do not radiate outward like the spokes of a wheel. They curve. They wind outward from the center of the galaxy in long, graceful arcs, each one bending gently as it reaches into the outer disk. And if you could see them from far enough away, they would look like the arms of a slow, vast, cosmic pinwheel, turning, always turning. Let us walk along these arms tonight, slowly. There is no hurry. The arms themselves are in no hurry. They have been winding through this galaxy for hundreds of millions of years, and they will continue long after this night is over. The Milky Way has 4 main spiral arms, and each one has a name. The 2 major arms are the Perseus arm and the Scutum Centaurus arm. They are the largest, the most massive, the most richly populated with stars and gas and dust. They attach to the ends of the great central bar that runs through the heart of the galaxy, stretching outward from there in long, curving sweeps. The two minor arms are the Sagittarius arm and the Norma arm. They are less massive than their two major siblings, containing fewer of the great clouds of hydrogen and fewer of the towering red giant stars, but they are still vast beyond any earthly measure, still winding, still turning, still full of stars beyond counting. And then there are the smaller structures, the spurs, the bridges, the minor arcs that reach between the great arms like quiet country paths connecting larger roads. The Orion Spur, where our own sun and solar system make their home, is one of these smaller features, a gentle offshoot branching from the region between the Perseus and Sagittarius arms, extending roughly 20,000 light years in length. A modest address in a grand neighborhood. The names of these arms carry a quiet poetry of their own. Perseus. In Greek mythology, Perseus was the hero who flew through the night sky on winged sandals, who carried the severed head of Medusa to turn his enemies to stone, who rescued Andromeda from the sea monster. He was a figure of swift, decisive motion through the dark. And the arm that bears his name stretches through the outer galaxy, beyond the sun, curving through constellations that have carried their ancient names for thousands of years. Scutum Centaurus. Scutum is the shield. Centaurus is the centaur, the wise half-man, half-horse of Greek legend, the great teacher of heroes. This arm, the galaxy's other major arm, winds through the inner galaxy, closer to the center, bright with young stars and dense with the raw material of future suns. Sagittarius, the archer. When we look toward the constellation of Sagittarius in the night sky, we are looking toward the center of our galaxy, past the near side of this arm, deep into the glowing heart of the Milky Way. Names given by people on a small blue planet to features so vast that a single arm stretches further than light can tens of thousands of years. And yet the names fit. They carry the arms the way a name carries a person, lightly and with a kind of care. Now let us think about what the spiral arms actually are, because they are not what they first appear to be. It would be natural to imagine the spiral arms as fixed structures, as solid bands of stars rotating together, the way the spokes of a wheel rotate as the wheel turns. But they are not. The spiral arms are not solid. They are not fixed. They are, in a deep and beautiful sense, something more like a pattern than a structure. The leading explanation is called density wave theory. Imagine a slow-moving truck on a busy highway. The cars behind the truck bunch up, crowding together as they slow down to match its pace. From above, you would see a region of dense, closely packed cars around the truck, trailing off into normal spacing ahead of and behind it. Now imagine the truck is moving very slowly, and the cars are moving much faster. Cars drive into the dense region slow, and then eventually emerge from the front of the jam and speed up again. The jam itself, the dense region, moves at the speed of the truck, but the individual cars move at their own speed, passing through the jam and out the other side. The spiral arms work in something like this way. The density wave, the pattern of slightly greater gravitational pull, rotates through the galaxy at its own speed. The individual stars and clouds of gas move at different speeds, most of them orbiting the galactic center faster than the density wave itself rotates. They pass through the arm, slowing a little as they enter the denser region, then emerging and moving on. The arm is not made of the same stars over time. It is a wave, a pattern, a slow pulse of compression moving through the disk of the galaxy. And it is in that compression that something remarkable happens. When a great cloud of gas and dust drifts into the leading edge of a spiral arm, the density wave compresses it, squeezes it gently, the way you might squeeze a handful of clay, causing it to pull together under its own gravity. And when a gas cloud is compressed enough, when enough material gathers in one place, gravity takes over completely. The cloud begins to collapse inward. It heats up. It rotates faster as it shrinks. The way a figure skater pulls their arms in and spins faster, and eventually, at the center of that collapse, the temperature and pressure rise high enough to ignite nuclear fusion. A new star is born. This is what the spiral arms do. They are nurseries. Long, curved, winding nurseries where new stars are brought into being by the patient compression of drifting gas. The bright, blue-white stars that trace the arms so vividly are the newborns. They formed only recently, in astronomical terms, triggered by the passage of the density wave. They burn hot and brilliant, illuminating the surrounding gas clouds with their fierce young light. Those illuminated gas clouds are called emission nebulae, and they are among the most beautiful things in the known universe. Great pillars and sheets and tendrils of glowing gas, lit from within by the stars that formed inside them, pale green and rose and deep red. The colors of ionized hydrogen and oxygen, hanging in the dark like slow, enormous flames that never quite burn out. The Orion Nebula, which you can just barely see with the naked eye on a clear night, appearing as a faint smudge below the belt of Orion, is one of these star-forming regions. It lies in our own Orion Spur, about 1,300 light-years away. Within it, right now, new stars are being born. Protostellar disks of gas and dust are slowly gathering and spinning, some of them perhaps already forming the first rough outlines of planetary systems. When you look at the Orion Nebula on a clear night, you are looking at the galaxy still building itself, still making new things, still doing what it has been doing for 13 billion years. The spiral arms are also home to the galaxies' most massive stars. These giants, called O-type and B-type stars, are dozens or even hundreds of times the mass of our sun. They burn so furiously, so extravagantly, that they consume their fuel in only a few million years. The sun, by comparison, has been burning for nearly 5 billion years and has roughly 5 billion more ahead of it. These massive stars are the mayflies of the galaxy. Brief, brilliant, consuming. And when they die, they do not go quietly. They explode. A supernova, the death of a massive star, releases more energy in a few weeks than our sun will release in its entire 10 billion year lifetime. It blasts the star's outer layers outward into the surrounding gas, and in that explosion, in that tremendous, violent scattering, the heavy elements forged in the star's core are spread across the arm. Carbon, oxygen, nitrogen, iron, silicon, the elements that will eventually find their way into new stars, new planets, new oceans, new living things. The spiral arms are not only nurseries, they are also forges, places where stars are made, burned, and unmade, and their remains scattered to become the raw material of what comes next. Somewhere in a spiral arm far from ours, right now, a massive star is nearing the end of its brief life. Its core, having burned through its hydrogen and helium and carbon, is building up a core of iron that cannot be fused, and soon, in the span of cosmic time, it will collapse and explode in a brief and brilliant flash. And the light from that explosion will travel outward through the arm, through the disk, through the dark, eventually perhaps reaching us thousands of years from now as a new point of light in our night sky. A star dying across the galaxy, its last light arriving here like a letter posted long ago. Let your breath slow a little. Let the image of those great winding arms drift gently through your mind, not as a diagram, not as a chart with labels and distances, just as a feeling, a sense of winding, of curving, of slow, enormous spirals turning in the dark, lit here and there by the brief, bright fires of young stars, humming with the quiet activity of gas clouds, slowly gathering, slowly becoming. You are inside one of those spirals right now. carried along its gentle curve at 800,000 kilometers per hour through a neighborhood that is billions of years old. And you are still, and you are warm, and the arms wind on without any effort at all. At the very heart of the Milky Way, before you reach the spiral arms, before you reach the dense molecular clouds, or the swirling chaos near the center, there is a structure that is easy to overlook. It does not announce itself. It does not blaze with the brilliant blue-white light of young stars. It does not erupt or flash or radiate in the dramatic ways that other parts of the galaxy do. It is quiet. It is old. And it is enormous. It is called the galactic bar, a long, straight concentration of ancient stars running through the very center of the galaxy, from one side of the inner disk to the other, not curved, not spiraling, just straight, like a slow axle through the heart of the great turning wheel. Let us sit with this structure for a while. Let its age and its stillness settle into the room. The bar stretches roughly 27,000 light years from end to end. That is a span so large that if you placed it alongside our entire neighborhood of the galaxy, it would dwarf it entirely. The distance from the sun to the galactic center is about 26,000 light years. The bar is longer than that entire journey. It runs through the center like a slow, enormous bridge, connecting the inner ends of the spiral arms at each of its tips. It sits at an angle relative to our position. If you drew a straight line from our sun to the galactic center, the bar would be tilted about 25 to 30 degrees from that line, not pointed directly at us, not pointed away, just slightly angled, the way a key rests in a lock before it turns. And this angle matters. It is part of why the bar was so difficult to see. For a long time, astronomers suspected that the Milky Way might have a bar at its center. Other barred spiral galaxies, seen from outside and far away, showed this feature clearly, a bright, elongated concentration of stars running through the middle, with the spiral arms curling outward from each end. Perhaps half of all spiral galaxies in the observable universe are barred spirals. But confirming the bar in our own galaxy was difficult. We are inside the galaxy. We cannot step outside and look at it from above. And the center of the Milky Way is hidden from ordinary visible light telescopes by thousands of light years of gas and dust. When you look toward the galactic center with your eyes, or with a visible light telescope, you see only the dust, a dark, obscuring veil between us and the heart of things. It was not until 2005 that the Spitzer Space Telescope, observing in infrared light that passes through dust the way heat passes through a thin blanket, finally gave astronomers a clear enough view to confirm the bar's true size and orientation. Infrared light is not visible to the human eye. It is the light of warmth rather than brightness. And it was this gentler, warmer kind of light that finally allowed us to see what had been at the center of our home all along. The stars of the galactic bar are old. They are not the brilliant blue-white giants of the spiral arms. They are not the hot, young stars that burn briefly and explosively. They are red giants and red clump stars, cooler and dimmer than the young stars of the disk, glowing with a warm amber and orange light, stars that formed long ago in the early history of the galaxy, when the universe was young and star formation was a furious, widespread activity rather than the quieter, more localized process it is today. Many of the stars in the bar are more than 10 billion years old. They formed before our sun existed, before the earth existed, before the solar system had even begun to condense from its cloud of gas and dust. These stars were already ancient when our world was born. Think of that for a moment. Stars that have been burning quietly and steadily since before the earth existed. Stars that watched from their slow orbits in the galactic center as our solar system gradually assembled itself, as the planets formed, as life slowly emerged on a small blue world in a quiet jagged spur of a spiral arm. They did not watch, of course. Stars do not watch, but they were there, patient and old and warm in the dark. The bar rotates, not the way a solid rod rotates, with every part turning at the same speed. The galaxy does not rotate that way. Instead, the bar has what astronomers call a pattern speed. The entire bar structure rotates as a pattern, making one full rotation roughly every 160 to 180 million years. 160 million years for a single rotation. At that pace, since the time the last non-avian dinosaurs walked the Earth, the galactic bar has completed barely one full turn. It is a motion so slow that it makes the word slow feel entirely inadequate. It is a turning measured not in seconds or minutes or years, but in geological epochs, in the rise and fall of entire branches of life on Earth. And yet it turns steadily, patiently, the way all things in the galaxy ultimately move, not with urgency, not with effort, just with the quiet, irresistible persistence of gravity. Within the bar, there is an even more interesting structure. Astronomers describe the inner part of the bar as having a boxy or peanut-shaped cross-section. When you look at it from the side, not as a long, thin rod, but as a three-dimensional object, it bulges outward above and below the galactic plane, creating a shape that is wider in the middle and pinched at the ends like a peanut, like two rounded lobes pressed gently together. This peanut shape is not an accident. It is the result of a phenomenon called buckling. Early in the bar's history, as stars orbited within its structure, certain resonances between their orbits caused the bar to become unstable in the vertical direction. Stars that had been moving in flat, horizontal paths began to bob upward and downward as they traveled. And over time, this collective bobbing thickened the bar in the middle, puffing it out into that distinctive boxy peanut shape. It is a shape produced entirely by by the gravitational interactions of hundreds of billions of stars over billions of years. No blueprint, no architect, just stars responding to each other's gravity slowly over time, producing something that looks almost deliberate. The bar also does something else of great importance. It acts as a kind of pump. As the bar rotates through the inner galaxy, it disturbs the orbits of the gas clouds in its vicinity. Gas that would otherwise settle into calm, circular orbits, is nudged and pulled into non-circular paths. It is pushed inward, channeled along the bar toward the galactic center. This funneling of gas feeds the region called the central molecular zone, a dense and active region of the inner galaxy, roughly 1,500 light years across. The central molecular zone contains an enormous concentration of molecular gas, the raw material for new stars. About 10% of the entire galaxy's total molecular gas is packed into this relatively small central region. The bar is feeding the center, slowly, continuously, channeling material inward the way a river channels water toward the sea. And in that central reservoir of gas, stars are forming densely and actively in a way that is quite different from the quieter star formation in the outer disk. Some astronomers have proposed that the Milky Way may actually contain two bars, a long, thin outer bar stretching those 27,000 light years from tip to tip, and nested within it a shorter inner bar oriented at a slightly different angle. Two overlapping structures of different sizes and different rotational speeds, one inside the other, like the hands of a clock that tick at different rates. This is still debated. The dust and gas that obscure the galactic center make it difficult to measure with the precision required to settle the question. But the possibility is a beautiful one, the idea that at the heart of our galaxy, hidden behind its veils of dust, there might be not one, but two turning bars, nested within each other in some intricate and ancient gravitational dance. orbits. There is something very peaceful about the galactic bar when you sit with it long enough. It is old, older than almost anything else we will visit on this journey. Its stars formed in the first great flush of stellar birth, when the young galaxy was dense and hot and feverishly active. And now they turn, slowly, quietly, still burning after all this time. Red and warm and patient in the dark at the center of things. The bar does not hurry. It does not change quickly. In a galaxy where stars are born and die, and new structures constantly form and dissolve and reform, the bar is one of the most enduring features, one of the oldest shapes in our cosmic home. It has been there since near the beginning of the Milky Way itself, turning in the dark, feeding the center, holding its ancient stars in slow and faithful orbits, while outside it, the spiral arms wind and unwind. New stars flash into being and burn out, and the whole great disk turns around it like a wheel turning on its axle. Let that image rest in your mind. The bar at the center, old and still and warm, everything else turning around it, and you, somewhere far out in one of those spiral arms, still and warm yourself, resting. There is a kind of kinship in that, a kind of quiet symmetry. Let your breath slow. Let the bar turn on in the dark at the heart of things. Let the galaxy do what it has always done, without any help from you at all. Every great structure has a center. A forest has a place where the oldest trees grow tallest, and the canopy is densest. An ocean has a deep calm far from every shore. A spiral has the point from which all its curves emerge, and toward which they seem to return. The Milky Way has a center too. It lies about 26,000 light years from where we are right now, in the direction of the constellation Sagittarius, low in the summer sky. You cannot see it with your eyes. You cannot see it with an ordinary telescope. It is hidden behind 26,000 light years of gas and dust, layer upon layer of the interstellar medium. A veil so thick that visible light cannot penetrate it. But it is there. It has always been there. The heart of our galaxy beating slowly in the dark. Let us travel toward it now. Gently. There is nothing to fear in this journey. We are moving in imagination only, carried on the quiet current of words. As we move inward, past the spiral arms, past the quieter regions of the disk, the sky around us changes. The stars grow more numerous. Not just more numerous, but dramatically so. In our own neighborhood near the sun, there are perhaps a few stars within a few light years in every direction. At the galactic center, the density of stars increases to something almost incomprehensible. In the innermost regions, stars are packed so closely together that the average distance between them shrinks to a fraction of a light year. The night sky from a planet near the galactic center would be blazing. Not the scattered, gentle field of lights we see, but a dense, glowing carpet of stars from horizon to horizon, so bright that true darkness might never come. But we are not looking for a planet tonight. We are drifting slowly, watching the star density increase around us as we move inward toward the center of things. We pass first through the outer regions of the galactic bulge, that rounded, amber-glowing concentration of ancient stars we described in an earlier section. The stars here are old, red and quiet. They have been orbiting the center of the galaxy for billions of years. Their paths long and looping, carrying them up and out of the plane of the disk and back down again in great slow arcs. Deeper still, we approach a region called the central molecular zone. The central molecular zone stretches more than 650 light years across, surrounding the very heart of the galaxy like a great, turbulent wreath of gas and dust. It is the most extreme neighborhood in the entire Milky Way. In February of 2026, astronomers using the ALMA telescope array, the Atacama Large Millimeter and Submillimeter Array, high in the Chilean desert, released the largest and most detailed image ever taken of this region. It revealed a landscape of extraordinary complexity. Dense filaments of cold gas flowing like slow rivers toward the center. Clumps of matter gradually collapsing into new stars, ancient star clusters, and the remnants of long ago explosions, all tangled together in a region so crowded and so active that it bears almost no resemblance to the quiet outer disk where our sun makes its home. The central molecular zone contains about 80% of all the cold, dense molecular gas in the entire galaxy. Most of the raw material for new stars in the Milky Way is gathered here. In this relatively small central region, a vast reservoir of potential, slowly stirring, slowly feeding inward. Within that reservoir, astronomers have identified more than 70 different types of molecules drifting through the gas. Not just simple molecules, not just hydrogen or helium, but complex organic molecules, ethanol, methanol, silicon monoxide, long chains of carbon and hydrogen tumbling slowly through the dense gas clouds of the galactic center. The chemistry of the central zone is richer, stranger, and more varied than almost anywhere else in the galaxy. Organic molecules in the heart of the Milky Way, building blocks of the kind that, under the right conditions, can become the building blocks of life. Drifting in the gas clouds at the very center of our cosmic home, hundreds of light years from the nearest planet. It is a quiet reminder that the universe does not wait for the right conditions before beginning to build the ingredients of complexity. It builds them everywhere, even in places where life itself could never take root, even in the roiling, dense, radiation-bathed heart of a galaxy. The stars of the central molecular zone are unlike any others in the galaxy. They are among the most massive stars known, giants that form quickly from the dense gas clouds, burn furiously, and die young. Many of them are tens or even hundreds of times the mass of our sun. They live for only a few million years before exploding in tremendous supernovae. and sometimes in even more violent events called hypernova. Explosions so powerful they release, in a fraction of a second, more energy than the sun will radiate across its entire 10 billion year life. These explosions seed the central gas with heavy elements. They send shock waves rippling through the central molecular zone, compressing some gas clouds and dispersing others. They are part of the endless, churning cycle of the galactic center, material falling in, stars forming, stars exploding, material scattering, and then falling inward again. Among the most remarkable of the central star clusters are the Arches cluster and the quintuplet cluster. The Arches cluster, just 100 light years from the very center of the galaxy, is one of the densest known star clusters in the entire Milky Way. It contains over 100 massive, luminous stars packed into a region only a few light years across. A concentration of stellar fire that, from the right vantage point, would appear as a single brilliant knot of light, stretching above and below the plane of the Milky Way's disk, rising from the galactic center like two vast, slow exhalations, are structures called the Fermi bubbles. The Fermi bubbles were discovered in 2010 when astronomers analyzing data from NASA's Fermi Gamma Ray Space Telescope noticed two enormous lobes of gamma ray emission extending above and below the galactic center. Each bubble stretches roughly 25,000 light years from the center. Together, they span 50,000 light years, half the full width of the Milky Way's disk, rising like two enormous breath clouds in the cold. What caused them is still a matter of careful study, but astronomers believe the most likely explanation is that the supermassive black hole at the galaxy's center, Sagittarius A, was far more active in the relatively recent past, perhaps a few million years ago. It consumed a large amount of material and released a tremendous burst of energy. That energy drove gas outward from the center in all directions, and the great bubbles we see today are the still expanding remnant of that ancient outburst. A black hole exhaling, the breath still rising millions of years later. There is also the radio arc, running perpendicular to the plane of the Milky Way near the galactic center, is a remarkable structure of parallel filaments called the galactic center radio arc. It was discovered in the 1980s and has puzzled astronomers ever since. The filaments are extraordinarily straight, running for hundreds of light years in near-perfect parallel lines, glowing in radio wavelengths. They are thought to be produced by electrons spiraling along magnetic field lines. The galactic center has an unusually strong and ordered magnetic field threading through the gas. And where that field is strong and straight, the electrons follow it faithfully, producing the ghostly radio filaments we can detect with our telescopes. Hundreds of these filaments have now been identified, crisscrossing the inner regions of the galaxy in a web of invisible magnetic structure made faintly visible by the particles threading through it, like the lines of iron filings around a magnet. But each filament hundreds of light years long, running through the heart of the galaxy in slow and silent order. All of this, the dense gas, the massive stars, the Fermi bubbles, the radio filaments, the ancient clusters, and the exploding supernovae, all of it surrounds and swirls around a single point. A single point at the very center of everything. A point called Sagittarius A. We will visit that point in the next section. We will sit quietly with the sleeping giant at the heart of our home. But for now, let us simply acknowledge it. Let us feel its presence at the center of everything we have been describing, all the winding arms, all the drifting gas, all the old stars in the bar and the bulge, all the ancient globular clusters in the halo, all the billions of stars in the disk. Every single one of them is, in some slow and fundamental sense, orbiting that point. The whole galaxy turns around one place. And right now, you are resting, still and warm, 26,000 light years away from the center of your own galaxy, carried in a slow orbit around something you will never see with your naked eyes, connected to it nonetheless, part of the great turning. Let your breath slow. Let the galactic center glow quietly in your imagination. Let the filaments drift. Let the gas clouds flow slowly inward. Let the massive stars burn briefly and brilliantly in the dark. All of it turning, all of it patient, all of it held together by the same quiet force that holds you gently to the earth right now. At the very center of everything we have described, at the still point around which the bar turns and the spiral arms wind, and the hundreds of billions of stars of the Milky Way make their long, faithful orbits at the heart of our galaxy. There is something that cannot be seen, something that swallows light rather than emitting it, something whose presence is known not by what it shows us, but by what it does to everything around it. It is called Sagittarius A, pronounced Sagittarius A star, named for the constellation in whose direction it lies. The asterisk, the little star symbol in its name, is a convention from the notation of radio astronomy, where an asterisk denotes a particularly bright radio source. It is a gentle irony that the thing at the center of our galaxy, the thing around which everything turns, the thing we spent decades trying to confirm and to see, should carry in its name a symbol that means star, because a star is a thing of light. And Sagittarius A is a place where light does not escape at all. Let us sit with it quietly tonight. There is nothing frightening here, only something ancient and massive and very, very still. Sagittarius A is a supermassive black hole. Its mass is approximately 4 million times the mass of our sun. 4 million suns worth of matter compressed into a region with a diameter of roughly 23.5 million kilometers. 23.5 million kilometers sounds large, but consider that the sun itself is nearly 1.5 million kilometers across, and and the distance from the Earth to the Sun is 150 million kilometers. So the event horizon of Sagittarius A, the boundary within which nothing can escape, is smaller than the distance from the Earth to the Sun. It is smaller, in fact, than the orbit of Mercury. 4 million solar masses compressed into a space smaller than Mercury's orbit. It is an almost impossible compression, a density so extraordinary that space and time themselves are profoundly distorted in its vicinity. The rules that govern the rest of the universe bend near Sagittarius A in ways that only the mathematics of general relativity can describe. For decades, astronomers suspected that something massive and dark lay at the center of the Milky Way. The way stars moved near the galactic center, the strange radio emissions, the intense activity of the gas clouds, all pointed toward something extraordinary, but confirming it and seeing it required patience and ingenuity. The first patient step was taken by 2 independent teams of astronomers who spent years carefully tracking the movements of individual stars near the galactic center. These stars, called S-stars, orbit the central point of the galaxy in tight, elliptical paths, completing full orbits in periods ranging from a few years to a few decades. One of them, called S-2, completes its orbit in approximately 16 years. By watching S-2 and its fellow S-stars wheel around the central point year after year, astronomers were able to calculate exactly how much mass must be concentrated at that point to produce such rapid, tight orbits. The answer was unambiguous. 4 million solar masses in a region no larger than our inner solar system. Nothing but a black hole could produce such an effect. This work, led by Reinhard Genzel at the Max Planck Institute and Andrea Ghez at UCLA, earned both researchers a share of the 2020 Nobel Prize in Physics. Decades of careful, painstaking observation, watching stars circle something invisible, confirming by the geometry of their paths that a sleeping giant resided at the center of our home. Then in May of 2022 came the image. The Event Horizon Telescope Collaboration, a global network of radio telescopes linked together to function as a single Earth-sized instrument, released the first direct image of Sagittarius A. It was not a photograph in the ordinary sense. Radio telescopes do not capture light the way a camera does. But what the collaboration produced, after years of observation and extraordinary computational effort to process the data, was an image that showed exactly what the physics predicted: a bright, glowing ring of superheated gas and material surrounding a dark central shadow. The shadow of the event horizon itself, the place where light bends around the black hole's gravity and cannot escape. The ring glows orange and amber. The shadow at its center is dark, and the entire structure, the ring, the shadow, everything, is only about 50 microarcseconds across in the sky. To put that in perspective, it is like trying to photograph a donut placed on the surface of the moon. The resolution required was extraordinary, possible only by linking telescopes on every continent, including one at the South Pole, into a single coordinated instrument as wide as the Earth itself. What makes Sagittarius a particularly remarkable in the context of the wider universe is how quiet it is. Supermassive black holes can be extraordinarily active when they consume large amounts of gas and dust. The material spiraling inward heats to tremendous temperatures and releases enormous energy. A sufficiently active black hole produces what astronomers call an active galactic nucleus, or AGN. Some AGNs are among the brightest objects in the observable universe, quasars, which are intensely active galactic nuclei seen in the distant universe, can outshine their entire host galaxies by factors of hundreds or thousands. Sagittarius A is not like that. Not today. Today, Sagittarius A is mostly dormant. It occasionally consumes small amounts of gas or dust, producing brief flares of X-ray or infrared radiation that last for minutes or hours. But between these flares, it is quiet. It sits at the center of the galaxy, vast and patient and still, not currently consuming anything significant, not radiating dramatically, not launching jets of material into the surrounding space. For a 4 million solar mass black hole, it is remarkably, almost surprisingly, calm. But it has not always been this quiet. The Fermi bubbles we described in the last section, those two enormous lobes of gamma ray emission, stretching 25,000 light years above and below the galactic center, suggest that within the last few million years, something dramatic happened here. The most likely explanation is that Sagittarius A consumed a large amount of material in a relatively short period of time. Perhaps a large gas cloud fell into the black hole. Perhaps a burst of intense star formation in the central region fed a great deal of material inward. Whatever the cause, the result was an outburst of energy so powerful that it drove gas outward from the center in two vast plumes. And those plumes are still expanding today, slowly and silently, into the surrounding halo. A few million years ago, from a planet somewhere outside the Milky Way, our galaxy's center would have blazed briefly with unusual intensity. A flicker of activity from the sleeping giant, visible across the universe, and then gone. There is a community of stars that lives in extraordinary proximity to Sagittarius A. Within just 3 light years of the black hole, there are thousands of stellar mass black holes, the remnants of massive stars that lived their brief, brilliant lives near the galactic center and then collapsed. They orbit the supermassive black hole in a dense swarm, invisible individually, but detectable through their collective effects. A galaxy within a galaxy of darkness, and within a fraction of a light year of Sagittarius A, something even stranger. A small cluster of young, massive stars called the S-cluster, orbiting the black hole at tremendous speeds. Estwo, the star whose orbit was tracked to confirm the black hole's mass, travels at about 3% of the speed of light at its closest approach. 3% of the speed of light, moving so fast that its orbit is visibly distorted by the effects of general relativity. Its path shifting slightly with each pass in a way that matches Einstein's equations almost perfectly. Nature conducting a physics experiment at the center of our galaxy. And the experiment keeps confirming the same beautiful equations over and over. What lies beyond the event horizon? Beyond that dark boundary in the glowing ring of the first image? No one knows with certainty. The physics of the very center of a black hole, the singularity, where the known equations of physics break down and produce infinities, remains one of the great open questions of science. General relativity and quantum mechanics, the two great frameworks through which we understand reality at the largest and smallest scales, do not yet speak the same language at the singularity. A complete theory of quantum gravity, one that could describe what happens at the center of a black hole, remains one of the deepest unsolved problems in all of physics. The inside of Sagittarius A is, in the most literal sense, unknown. A mystery at the heart of our home. A question the universe is not yet ready to answer. And perhaps that is as it should be. Not everything needs to be understood tonight. Some things are allowed to remain mysterious, to remain dark and quiet at the center of things, holding their secrets while the rest of the galaxy turns slowly around them. Sagittarius A does not need us to understand it. It has been sitting there, patient and massive and dark, for billions of years, long before there were eyes to look for it, long before there were minds to wonder about it, long before the S-stars began their tight, faithful orbits, or the first radio telescopes turned their ears toward the constellation Sagittarius. It will still be there long after tonight, long after all of us, quiet at the center everything in its slow and patient gravity. Let that thought be a comfortable one. The center is held. Everything turns around something stable and ancient and still. You too are still right now, and warm and held, and the giant sleeps on in the dark at the heart of the galaxy, as it has always done, as it will always do. Imagine you are standing at the edge of a very old city at night. The city glows behind you. The streets and buildings, the lights in windows, the hum of activity, all of it gathered in the warm center. But as you walk away from the city, out into the surrounding countryside, the light fades, the noise softens, and eventually you find yourself in a kind of quiet dark that the city itself has almost forgotten. But even here, in the quiet, there are lights. Not the bright clustered lights of the city, just scattered, solitary glimmers. A farmhouse here, a distant window there. Old lights in old places, burning steadily in the surrounding dark. The stellar halo of the Milky Way is something like that. It is the part of our galaxy that surrounds everything else. A vast, roughly spherical region extending far beyond the disk, far beyond the spiral arms, far beyond even the outermost stars of the thick disk. It does not glow with the density of the galactic center or the brightness of the spiral arms. It is sparse, it is quiet, and it is very, very old. Let us drift out into it now, slowly, away from the disk, into the surrounding dark. The stellar halo of the Milky Way extends somewhere between 300,000 and perhaps 1 million light years from the galactic center in all directions. To put that in perspective, the disk of the galaxy that we have spent so much time describing, with all its spiral arms and star-forming regions and dense gas clouds, is only about 100,000 light years across and 1,000 light years thick. The halo is far, far larger. It dwarfs the disk the way an ocean dwarfs an island. And yet, for all its size, the halo contains remarkably little. The stars of the halo represent only about 1,000th of the Milky Way's total stellar mass. 1,000th. All that volume, all that space, and only a tiny, scattered handful of stars. This is what makes the halo so different from the disk. In the disk, stars are neighbors. They live in the same neighborhood, separated by a few light years, breathing the same interstellar medium, born from the same spiral arm gas clouds. In the halo, stars are solitary, separated by vast distances, moving in long, looping, often tilted orbits that carry them far above and below the plane of the disk, out into the surrounding dark, and then slowly back again. The stars of the halo are ancient. Most of them are more than 10 billion years old. Many of them are 11 or 12 billion years old. Some of the very oldest, discovered only in recent years, formed between 12 and 13 billion years ago, in the earliest epoch of the universe, when the very first galaxies were just beginning to take shape. In 2024, a team of astronomers at MIT, led by astrophysicist Anna Frebel, identified 3 extraordinary stars in the Milky Way's halo. These stars, which they called SAS stars, standing for small accreted stellar system stars, were found to be between 12 and 13 billion years old. What made them particularly remarkable was not just their age, but their chemistry. These stars contain almost none of the heavier elements that later generations of stars would produce and scatter through the galaxy. One of them contains less than 1/10,000th the amount of iron relative to hydrogen that our sun contains. They are chemically almost pristine, almost as simple as the universe was when they formed, made mostly of hydrogen and helium, with only the faintest trace of heavier elements. Because when they were born, the universe had barely had time to forge anything heavier. These stars are, in the most literal sense, fossils, living records of a time before the Milky Way as we know it existed, before the disk formed, before the spiral arms wound their first slow curves, before the bar settled into place when the universe was young and the first small galaxies were just beginning to condense from the primordial gas. This brings us to one of the most beautiful things about the stellar halo: the story it tells about how the Milky Way was built. Our galaxy did not form all at once. It did not appear fully formed in a single moment of cosmic birth. It grew. It assembled itself over billions of years through a process of slow accretion, absorbing smaller galaxies and star clusters that strayed too close and were captured by its gravity. The stellar halo is the record of that assembly. When a small dwarf galaxy falls into the Milky Way's gravitational field, it does not simply crash and merge cleanly. The Milky Way's gravity stretches it, pulls it apart, draws its stars into long, thin streams that wrap around the galaxy, dispersing gradually over millions of years into the surrounding halo. These streams are still there, ghostly ribbons of stars moving together through the halo, sharing the same velocity and the same chemistry because they once belonged to the same small galaxy. Astronomers have identified dozens of these stellar streams in the halo of the Milky Way. They have names. The Sagittarius stream, the longest and most prominent, stretches almost completely around the entire galaxy. The dispersed remains of the Sagittarius Dwarf galaxy, which the Milky Way has been slowly absorbing for billions of years. The Helmy streams, the Orphan stream, each one a ghost, each one the memory of a smaller galaxy that no longer exists as a separate entity. Its stars now drifting, scattered and solitary, through the outer halo of the galaxy that consumed it. The halo also contains some of the most ancient structures in the Milky Way. Scattered through the halo, in slow orbits that carry them above and below the disk, in great looping paths, are the globular clusters. We will spend more time with these in the next section, but let us acknowledge them here as we drift through the halo. They appear as faint, slightly fuzzy points of light to the naked eye. A few of them are visible without a telescope on a very clear night, each one is a dense, ancient swarm of hundreds of thousands, or even millions of stars, packed into a sphere only a few dozen light years across. The Milky Way has about 150 known globular clusters distributed throughout the halo and the inner galaxy. They are among the oldest objects in the universe, some of them formed more than 13 billion years ago, when the universe itself was less than 1 billion years old. They are not remnants of absorbed galaxies, though some may be. They are structures that formed in the earliest epoch of the Milky Way's assembly, when dense clumps of primordial gas collapsed directly into tight, brilliant swarms of stars. They have been orbiting the galaxy ever since, patient and ancient, carrying within them some of the oldest starlight in the observable universe. There is something called the dual halo. Astronomers have found evidence that the Milky Way's stellar halo is not a single, uniform structure, but two overlapping populations, an inner halo and an outer halo. The inner halo, extending out to about 50,000 light years, is more flattened, more concentrated toward the plane of the disk. Its stars are somewhat metal richer, relatively speaking, containing slightly more of the heavy elements than the outer halo stars. The stars of the inner halo are approximately 11.5 billion years old. They formed during the period when the Milky Way was actively assembling itself, growing through the merger of smaller galaxies. They were born in the process of collision and accretion, formed in the turbulent in-between spaces where galaxies were mixing and merging. The outer halo, stretching beyond 50,000 light years, tells a different story. Its stars are more metal-poor, more ancient, moving in more randomly oriented orbits, many of them in retrograde, moving in the opposite direction to the general rotation of the galaxy. These are the stars that were captured most recently, or that belonged to very ancient dwarf galaxies, absorbed long ago at random angles. The SAS stars that MIT's team identified are part of this outer halo population, stars that once belonged to their own tiny galaxies, each of them alone now in the dark, orbiting the Milky Way in paths that still carry the memory of the direction their original galaxy was traveling when it was absorbed. Out here in the outer halo, in the deep surrounding dark far from the disk, the sky would be profoundly different from what we know. There would be no Milky Way band stretching across the sky. We would be too far from the disk to see it as a band. Instead, the galaxy's disk would appear below us if we were above the plane as a faint oval glow, a luminous smear in the darkness, containing hundreds of billions of stars, all of them so far away that they would blend into a soft, unresolved haze. Our home, seen from outside, a spiral, perhaps, an ellipse, a glow in the dark that is somehow impossibly familiar. And around us, in all directions, the deep dark of intergalactic space. A few scattered stars, our fellow halo inhabitants. Perhaps a distant globular cluster, visible as a faint knot of light. And beyond that, other galaxies, Andromeda, a faint elongated smear. The Magellanic clouds, bright and close. And behind them, stretching to the limit of what any eye could see, the vast, dark, scattered cosmos. The halo is where the Milky Way ends and the universe begins. It is the threshold, the quiet border between our home and everything beyond. And it is populated by the oldest witnesses, stars that have been drifting here since before the galaxy had a shape, since before there was a disk to orbit, since the universe itself was young and dense and building its first great structures from the dark. They are still here, still burning quietly in the surrounding dark. Let that thought settle around you like something old and gentle. You are resting. The halo drifts on outside. The ancient stars trace their long, slow orbits through the dark, carrying the memory of the galaxy's very first days. All of it patient, all of it enduring, all of it still. Picture an island, a large island, not a continent or an archipelago, just a single small island sitting quietly in the middle of a very large and very dark ocean. It has its own weather, its own birds, its own particular quality of light in the evening. It is self-contained, complete, a world within itself, surrounded on all sides by deep, quiet water. Now imagine that island is made of stars. Hundreds of thousands of stars packed together in a sphere only 100 light years across, drifting slowly through the halo of the Milky Way, far from the disk, far from the spiral arms, alone in the surrounding dark, orbiting the galaxy the way a moon orbits a planet, faithful, patient, enduring. This is a globular cluster, and our galaxy has about 150 of them, each one an island of old light, scattered through the deep surrounding dark of the halo, each one carrying within it hundreds of thousands or millions of stars, most of them older than almost anything else in the known universe. Let us visit a few of these islands tonight. Slowly. There is nowhere to be but here. The word globular comes from the Latin for sphere, and a globular cluster is, at first approximation, remarkably spherical. Not a flat disk like the galaxy itself, not elongated, not irregular in the way that open star clusters in the disk are, just a sphere, a great rounded ball of stars, denser at the center and fading toward the edges like a soft glow that brightens as you approach its heart. This spherical shape tells us something important about globular clusters. They are very old. When a collection of stars is young, it tends to be irregular. The gas cloud from which it formed was turbulent and asymmetric, and the young stars inherit that disorder. But over billions of years, the mutual gravitational interactions between the stars slowly, gently smooth things out. The cluster relaxes into its most comfortable shape. The most massive stars settle toward the center. The less massive stars drift outward, and the whole structure becomes gradually more and more spherical, more and more settled, more and more like itself. The deeply spherical shape of a globular cluster is the shape of age, the shape of billions of years of quiet settling. The oldest globular clusters in the Milky Way are more than 13 billion years old. The universe itself is approximately 13.8 billion years old. These clusters formed when the universe was less than 1 billion years in existence, when the very first large structures were assembling from the primordial gas, before most galaxies had taken their final shapes, before the disk of the Milky Way had formed, before the spiral arms had wound their first slow curves. The stars within the oldest globular clusters carry the chemical signature of that early time. They are metal poor, not poor in the sense of lacking value, but poor in the astronomical sense of containing very few of the heavy elements, the metals as astronomers call them, that were not present in abundance in the early universe. The early universe contained almost only hydrogen and helium. Heavier elements, carbon, oxygen, iron, calcium, had to be forged in stellar cores and scattered by supernovae over billions of years. The stars of the oldest globular clusters formed before that process had proceeded very far. They are made of a universe that was still mostly young and simple. Let us visit the most magnificent of these islands, Omega Centauri. Omega Centauri is the largest and most massive globular cluster in the entire Milky Way. It contains approximately 10 million stars packed into a sphere about 150 light years across. It is located about 17,000 light years from Earth, in the direction of the southern constellation Centaurus. On a clear night in the southern hemisphere, it is just barely visible to the naked eye as a faint, fuzzy star, slightly larger than a point of light, slightly softer at the edges than a true star. But through even a modest telescope, Omega Centauri becomes something extraordinary. A great, glowing sphere of stars, densest at the center and gradually softening toward its edges, like looking into a three-dimensional cloud of light. Hundreds of thousands of stars visible as individual points, and behind them, hundreds of thousands more too tightly packed and too distant to resolve individually, blurring together into a soft, continuous glow. Omega Centauri contains multiple populations of stars of different ages and different chemical compositions. This complexity has led some astronomers to suggest that Omega Centauri may not be a true globular cluster at all, but rather the stripped core of a dwarf galaxy that was captured by the Milky Way long ago, a galaxy within a galaxy. Its outer stars long since scattered into the halo, only its dense, brilliant heart remaining, still orbiting the Milky Way in a looping, tilted path that takes it as far as 18,000 light years above the plane of the disk before curving back down again. Now let us drift gently toward another island. 47 Tucani. 47 Tucani is the second brightest globular cluster in the sky. It lies about 14,500 light years from Earth, in the direction of the southern constellation Tucana. In the southern sky, it appears almost adjacent to the small Magellanic Cloud, though in reality it is more than 15 times closer to us than that dwarf galaxy. 47 Tucani can be seen with the naked eye under dark skies, appearing as a faint star of about the same apparent size as the full moon. Through a telescope, it reveals a breathtaking core, brilliantly dense and bright, surrounded by a softer, more dispersed halo of individual stars fading gently outward. It is approximately 12 billion years old. Its stars appear in two populations, the older of which formed about 12 billion years ago, and a slightly younger population, only 100 million years its junior. It contains millions of stars spread across a volume 120 light years across, and within it, astronomers have found at least 35 millisecond pulsars, collapsed stellar remnants spinning hundreds of times per second. extraordinary, tiny, furiously rotating objects nestled within the ancient, serene structure of the cluster. The very old and the very extreme, sharing the same island. Globular clusters move through the galaxy in great looping orbits. Unlike the stars in the disk, which move in roughly circular orbits, staying within the plane of the galaxy, globular clusters travel in highly elliptical paths. Their orbits carry them far out into the halo, above and below the plane of the disk, and then back inward, sometimes passing directly through the disk itself on their long journeys around the galactic center. Each time a globular cluster passes through the dense disk of the galaxy, it experiences something called a disk shocking. The rapidly changing gravitational field of the disk pulls at the cluster as it passes through, stretching it slightly, tugging at its outer stars, gradually loosening the cluster's gravitational grip on its most distant members over billions of years. This slow process of disk shocking has been dismantling the outer edges of globular clusters, scattering their stars into long, thin tidal tails that trail behind and ahead of the cluster like slow, dissolving wakes. Some globular clusters have been so thoroughly disrupted over billions of years that they no longer exist as distinct objects at all. They have been completely pulled apart by the galaxy's tidal forces, their stars dispersed into long streams that now trace ghostly arcs through the halo. In 2020, astronomers discovered evidence of one such cluster that was torn apart approximately 2 billion years ago. Its remains, forming a faint ring of metal-poor stars, wrapped all the way around the entire Milky Way, a necklace of ancient starlight, the memory of an island that no longer exists. The night sky from within a globular cluster would be unlike anything we can see from Earth. Within the dense core of a cluster, stars are separated by perhaps 1/10 of a light year on average, less than 100th of the typical distance between stars in our own neighborhood. The night sky from a planet near the core of a cluster would contain thousands of stars bright enough to cast faint shadows. The total starlight would be perhaps 100 times brighter than our own Milky Way sky. On a clear night, the sky would never be truly dark. There would always be a soft, ambient glow coming from no single source, but from all directions equally. A perpetual twilight of starlight, gentle and ancient. No human eye has ever seen such a sky, but there may be planets in globular clusters, old beyond measure, that have known no other kind of night. There is a quality to globular clusters that is hard to describe without reaching for the word peace. They are not the dramatic, active star-forming regions of the spiral arms. No new stars are being born in globular clusters. Their gas, if they ever had much, was used up long ago. The stars that remain have settled into their long Middle Ages and Old Ages. Red giants and yellow stars and dim, long-lived red dwarfs burning steadily in the dark. No explosions, no great clouds of churning gas, no fierce young blue stars burning themselves out in a few million years. Just old stars, quietly burning, orbiting each other in their dense, settled sphere, having circled the galaxy hundreds of times over billions of years, wearing the shape of their long experience in their rounded, settled, deeply spherical form. Islands of old light, each one a quiet world apart, each one ancient enough to have been present at nearly the very beginning of the galaxy's long story. And they are still there tonight, right now, while you are resting. 150 islands of old light drifting in their slow orbits through the dark surrounding halo. Patient, enduring, luminous in a quiet, amber, ancient way. Let them glow gently at the edge of your imagination. Let their light be soft and warm. Let the deep, settled age of them settle into you. You are resting. The clusters drift on. The oldest light in the galaxy burns quietly in the dark, as it has for 13 billion years, and will continue to do for billions more. Everything we have described so far, you could, in principle, see. With the right telescope, with the right wavelength of light, the spiral arms glowing with the blue light of young stars, the galactic bar warm and amber in infrared, the dense star fields of the central molecular zone, the scattered ancient points of the halo stars, the globular clusters, each one a soft sphere of light drifting in the dark, all of it made of the same fundamental stuff, ordinary matter, protons and neutrons and electrons, atoms, the same basic ingredients as the ground beneath you and the air around you, and every star in every galaxy in the observable universe. But here is the quiet truth at the heart of the Milky Way, and at the heart of the entire cosmos. Everything we have described makes up less than 15% of the mass of our galaxy. The other 85% or more is something we cannot see, cannot touch, cannot detect with any electromagnetic telescope. Something that emits no light, absorbs no light, reflects no light. Something that interacts with ordinary matter only through gravity. We call it dark matter, and it is the invisible embrace that holds the Milky Way together. Let us rest with this idea for a while. It is not a frightening idea. It is, if you let it settle quietly, one of the most beautiful and mysterious things we know about the universe we live in. The story of how we discovered dark matter is, in large part, the story of one woman and her careful, patient attention to the night sky. Her name was Vera Rubin. As a child growing up in Washington, D.C., Vera Rubin would lie awake at night, watching the stars move slowly across her bedroom window. By the time she was 12, she had built her own telescope from cardboard tubes and lenses. She spent so much time watching the stars that her father eventually helped her build a better one. She became an astronomer, and in the 1970s, working with her colleague Kent Ford at the Carnegie Institution, she undertook a careful, methodical study of how stars move within spiral galaxies. The question she was asking seemed straightforward. How fast do stars orbit the center of a galaxy? And does that speed change with distance from the center? The expected answer, based on the known laws of gravity, was clear. Stars near the center, where most of the visible mass of a galaxy is concentrated, should orbit quickly. Stars in the outer regions, far from the center, should orbit more slowly. Just as the planets in our solar system orbit more slowly the further they are from the sun, Mercury is fast. Neptune is slow. This pattern, called a Keplerian decline, after Johannes Kepler, who first described the mathematical relationship between orbital speed and distance, should apply to galaxies just as it does to solar systems. But that is not what Vera Rubin found. Galaxy after galaxy, the rotation curves were flat, not declining, not falling off at the outer edges the way physics predicted. Flat. The stars in the outer regions of spiral galaxies were moving at approximately the same speed as the stars near the center, sometimes even faster than expected, as if there were far more mass in the outer regions of each galaxy than the visible stars and gas could account for. By 1980, Rubin and Ford had analyzed the rotation curves of 21 spiral galaxies. Every single one showed the same flat curve. The evidence was unambiguous. There was something massive in the outer regions of these galaxies that was not visible. Something providing the extra gravitational pull needed to keep the outer stars moving so fast without flying off into intergalactic space. Vera Rubin's calculations showed that galaxies must contain roughly 10 times as much invisible mass as visible mass. 10 times. For every star, every gas cloud, every dust grain that we can see and measure and catalog, there are approximately 10 times that amount of mass in some form we cannot detect at all. The luminous matter, the stars and gas that we see, are merely the visible tracers of a much larger, much more massive invisible structure surrounding each galaxy. In the Milky Way, the dark matter does not sit only in the outer halo, though it is most dominant there. It surrounds the entire galaxy in a great, roughly spherical cloud, vastly larger than the disk itself, extending perhaps 500,000 light years or more in every direction from the galactic center, an enormous, invisible sphere within which the visible galaxy sits like a bright ember within a vast, dark fog. This structure is called the dark matter halo. It is not empty. It is not simply an absence. It has density. It has mass. It has gravitational effects that are real and measurable and consistent with everything we observe. It is as real as the disk, or the bar, or the spiral arms. It is simply invisible to every instrument we have that relies on light. The dark matter halo of the Milky Way is estimated to contain somewhere between 500 billion and 2 trillion solar masses of material. Compare this to the total mass of all the visible stars in the Milky Way, which is estimated at somewhere around 50 to 60 billion solar masses. The dark matter outweighs the visible stars by a factor of perhaps 10 to 20 or more. All of that mass, invisible, surrounding everything, holding everything in place. What is dark matter exactly? That question is one of the deepest open questions in all of science. We know what it is not. It is not ordinary matter made of protons and neutrons, simply in a dark form. Not black holes in large numbers. Not cold gas clouds. Not burned out stars. All of these have been carefully considered and ruled out, or found to be insufficient to account for the observed effects. Dark matter is something genuinely different from anything we have directly detected in a laboratory. The leading candidates are hypothetical particles with names that carry the quiet poetry of theoretical physics. WIMPs, weakly interacting massive particles. Axions, extremely light particles originally proposed to solve a problem in the theory of the strong nuclear force, sterile neutrinos, hypothetical cousins of the neutrinos we do know about, but far more massive and far less interactive. None of these have been definitively detected. Experiments deep underground, in converted mines and tunnels, shielded from the constant rain of cosmic ray particles that would obscure a dark matter signal, have been searching for WIMPs for decades. They have set ever tighter limits on what a WIMP can be. They have ruled out enormous regions of possibility, but they have not yet announced a detection. Dark matter continues to reveal itself only through its gravity, only through the patient, indirect evidence of flat rotation curves, of gravitational lensing, of the motions of galaxies within galaxy clusters, always at a remove, always inferred rather than directly seen. There is something deeply meditative about dark matter. If you let yourself sit with it quietly, it is the most abundant form of matter in the universe. 5 times more dark matter than ordinary matter in the cosmos as a whole. It formed the first large structures in the universe, the great scaffolding of dark matter filaments, along which ordinary matter later gathered to form galaxies and galaxy clusters. Without dark matter, the universe would look entirely different. Galaxies would not have formed as they did. Stars would not exist in the numbers they do. The Milky Way, with all its beauty and complexity, would not be here. And yet it passes through you right now. Every second, tens of thousands of dark matter particles, if the leading theories are correct, are passing through your body, through the room around you, through the earth beneath you. They interact with nothing. They leave no trace. They do not slow down or scatter, or produce any signal that any instrument we have built can yet detect. They simply pass through, drawn along their vast, slow orbits within the dark matter halo, indifferent to the ordinary matter they move through, as ghostly and silent as starlight falling on a closed eye. You are right now immersed in dark matter, and the Milky Way, everything we have described and will describe on this long, gentle journey is held together by it, cradled within it. The visible galaxy, the glowing disk, and the warm bar, and the ancient halo stars, and the orbiting globular clusters. All of it rests inside the dark matter halo, like something precious, held in an enormous, invisible hand. Not gripped, not confined, just held gently, the way gravity always holds, with patience and without effort, with a force that crosses any distance and acts between any two masses, however different, however far apart. The invisible embrace of dark matter is not cold or frightening. It is simply there, as it has always been, since before the disk formed, since before the first stars ignited, since the very early universe, when dark matter laid down the first faint scaffolding of structure from which everything else, every galaxy, every star, every planet, every living thing would eventually emerge. You are resting inside it, surrounded by it, held by it. It asks nothing of you. It simply holds, quietly, invisibly, in the dark. Every star that has ever burned in the history of the universe began in the same way. In the cold, in the dark, in a vast, drifting cloud of gas and dust so thin and so quiet that it would be invisible to the naked eye if you were standing inside it. A cloud that might be hundreds of light years across, containing millions of times the mass of our sun, and yet so diffuse, so gently sparse, that it would feel like almost nothing at all. These clouds are called molecular clouds, and they are the nurseries of the galaxy, the places where the Milky Way makes new suns. Every star that warms a world, every star that a poet has ever looked up at and named, every star that an ancient navigator has ever steered by, every star in every constellation, in every human culture that has ever lifted its eyes to the night, all of them began in one of these cold, quiet, drifting clouds. Let us drift into one together now, slowly, gently, like a leaf settling on still water. A molecular cloud is called molecular because at the cold temperatures inside it, atoms bond together into molecules. The most abundant molecule is molecular hydrogen. Two hydrogen atoms bonded gently together, drifting through the cold. But molecular clouds contain far more than just hydrogen. Over 100 different types of molecules have been detected within them. Water, ammonia, methanol, formaldehyde, even complex organic molecules, long chains of carbon and hydrogen assembled in the dark by chemistry that requires no warmth, no light, no living thing to direct it, just time and the quantum rules that govern how atoms and molecules behave when they drift close enough to interact. The temperature inside a molecular cloud is extraordinarily low, typically between 10 and 30 degrees above absolute zero. 30 degrees above the coldest temperature the laws of physics permit, cold in a way that is almost unimaginable. Cold enough that almost all molecular motion has slowed nearly to stillness. Cold enough that the cloud glows not in visible light, nor infrared, nor even radio waves, but only in the faintest microwave emissions, detectable only by the most sensitive radio telescopes. These are the coldest large structures in the known universe, and they are the places where everything begins. A giant molecular cloud can be anywhere from 10 to several hundred light years across, and can contain between 1,000 and 10 million times the mass of our sun. The Milky Way contains thousands of them, concentrated primarily in the spiral arms and in the central molecular zone near the galactic center. They are the raw material of the galaxy's ongoing story, the slow reserves of potential from which new stars will be drawn over millions of years. The galaxy forms new stars at a rate of roughly 2 to 3 solar masses worth of material per year. It sounds modest, but accumulated over billions of years, it has produced hundreds of billions of stars. And right now, in the molecular clouds of our galaxy, that process is continuing. New suns are being born while you rest, while you breathe slowly in the dark, while this quiet voice drifts through your mind. Somewhere in the Milky Way tonight, a gas cloud is crossing a threshold. A small, dense clump within the cloud has gathered enough mass that gravity has begun to win its slow argument with the outward pressure of the gas. The clump is beginning to collapse, and something new is beginning. The process of collapse is not violent at first. It is almost imperceptibly slow by human standards. A dense clump of gas within a molecular cloud, perhaps a few light years across, and containing a few solar masses of material, begins to contract under its own gravity. As it contracts, it heats up. Not enough to glow yet, just enough to slow the collapse a little. The way a pillow compresses when you lie on it, offering gentle resistance without stopping you from sinking in. This stage is called a Bach globule when seen from outside. A small, dark clump within a larger bright cloud, dense enough to block the light of the stars behind it. A dark oval or circle against the glowing gas, named for the Dutch-American astronomer Bart Bach, who first drew attention to them in the 1940s as likely sites of star formation. He was right. As the clump collapses further, it begins to rotate. It had some initial rotation from the turbulent motions within the parent cloud, and as it contracts, like a figure skater pulling their arms inward, it spins faster. Not dramatically, just a slow, increasing rotation that causes the collapsing gas to flatten slightly into a disc shape around the dense central core. The core grows denser and hotter. It begins to emit infrared radiation. It is now a protostar. Not yet a star. Not yet burning with nuclear fusion, but warm and growing and drawing in more material from the surrounding disk. Eventually, after perhaps 100,000 years of slow collapse, the temperature at the center of the protostar reaches approximately 10 million degrees Celsius. And in that moment, in that threshold of heat and pressure, something remarkable happens. Hydrogen nuclei, moving fast enough now to overcome the electrical repulsion that normally keeps them apart, begin to collide and fuse. Two hydrogen nuclei fuse to form helium, and in that fusion, a tiny amount of mass is converted directly into energy, according to the most famous equation in all of science. Energy equal to mass times the speed of light squared. The core ignites. The outward pressure of that fusion energy now balances the inward pull of gravity. The collapse stops, and what was once a cold, dark clump of gas in a molecular cloud is now a star, a new sun, burning steadily, warming the surrounding space, illuminating the remnants of the gas cloud from which it formed. The illuminated remains of that gas cloud, lit by the newborn star within, are among the most beautiful objects in the universe. We call them emission nebulae, and some of them are visible even from Earth, more than 1,000 light years away, as faint smudges of color in the night sky. The Orion Nebula lies about 1,300 light years from Earth, just below the belt of Orion, visible to the naked eye as a faint, soft smudge. Through a telescope, it becomes a luminous cloud of gas, pale green and rose and blue-white, lit from within by 4 young massive stars called the trapezium, burning so brilliantly that their ultraviolet light ionizes the surrounding hydrogen gas, causing it to glow. Within that glowing cloud, dozens of protostars are still forming. Their protostellar disks, the flat spinning rings of gas and dust from which planets will eventually assemble, are visible in the Hubble Space Telescope's images as small, dark oval silhouettes against the bright background of the nebula. You are looking at a solar system in its earliest hours. The Eagle Nebula lies about 5,700 light years from Earth in the constellation Serpents. It is home to one of the most iconic images in the history of astronomy: the pillars of creation. 3 great columns of gas and dust, each one several light years tall, rising from the surface of the molecular cloud like the fingers of an enormous, slow hand. The pillars are being sculpted by the intense ultraviolet radiation from a cluster of massive young stars that formed within the nebula. The radiation is gradually eating away at the gas, eroding the cloud from the outside inward, but within the densest parts of the pillars, where the gas is thick enough to shield the material inside from the radiation. New stars are still forming. Hidden within those great dark columns of gas, new suns are being born, even as the pillars themselves are slowly being destroyed. Creation happening inside dissolution. New beginnings inside gentle endings. The Carina Nebula is one of the largest and brightest star-forming regions in the entire Milky Way. It lies about 7,500 light-years from Earth in the southern constellation Carina, and it is roughly 500 times larger in actual area than the Orion Nebula. Within it, over a dozen stars of enormous mass burn furiously. Their combined radiation sculpting the surrounding gas into great pillars and ridges and glowing arches. One of them, Eta Carini, is one of the most massive and luminous stars known in the entire galaxy, burning perhaps 5 million times brighter than our sun, so unstable and so violent that in the 1840s it erupted without fully exploding, briefly becoming the second brightest star in the night sky before fading again. It remains a star on the very edge of its own destruction, likely to explode as a supernova within the next 100,000 years. Within the Carina Nebula, the star cluster Trumpler 14 is one of the youngest known star clusters in the galaxy, only about 500,000 years old. 500,000 years, the blink of an eye in cosmic time. These stars have barely begun. And there is something deeply comforting in all of this. The galaxy is still making stars, still building, still drawing new suns from its ancient reserves of gas and dust. It has been doing this for 13 billion years, and it is doing it right now, tonight. cold, dark clouds in the spiral arms, in the dense gas of the central molecular zone, in the illuminated chambers of the Carina and Orion and Eagle nebulae. New suns coming into being, new disks of gas and dust assembling around them, new planets, perhaps, forming slowly in those disks over millions of years, new worlds, new surfaces, new oceans, perhaps, and new skies, and who knows what else in time. The galaxy is not finished. It is not winding down. It is still in the middle of its great long work, still patient, still creative, still drawing something new and bright from the cold dark of a molecular cloud, just as it always has. Let your breath be slow and easy. Let the nurseries of the galaxy glow gently at the edge of your thoughts. Cold clouds, collapsing cores, new stars igniting in the dark, the galaxy making new suns the way it always has, quietly and without hurry, in the cold and patient dark. We have watched new stars being born. We have drifted through the cold, dark clouds, where new suns take shape from nothing more than gas and gravity and time. Now let us follow one of those stars on its long journey, from its first light, through its long, steady middle years, and into its gentle or dramatic ending, depending on how massive it happened to be when it first ignited. The life of a star is, above all else, a story about balance. From the very first moment nuclear fusion ignites in a star's core, two forces are in conversation. Gravity pulling everything inward, trying always to collapse the star to its smallest possible form, and the outward pressure of fusion energy pushing back, keeping the star open, keeping it breathing. For as long as the fuel holds, these two forces remain in balance. The star neither collapses nor expands. It simply shines, steadily, patiently, year after year, century after century, millennium after millennium. This long, stable, shining middle period is called the main sequence. And for most stars, it is the longest chapter of a very long story. Our own sun has been on the main sequence for approximately 4.6 billion years. 4.6 billion years of steady, patient burning. Every day, every hour of every year for 4.6 billion years, the sun has been fusing roughly 600 million metric tons of hydrogen into helium in its core every single second. 600 million metric tons every second, without pause, without interruption, for longer than the Earth has existed, and it has roughly 5 billion years more to go. The sun is a middle-aged star, not young and brilliant and brief like the great blue giants of the spiral arms, not tiny and dim and almost impossibly long-lived like the red dwarf stars that make up the majority of the galaxy's stellar population. Just a steady, warm, yellow-white star in a comfortable middle position, doing what it has always done, quietly and without drama. The most numerous stars in the Milky Way are not stars like our sun. They are red dwarfs. Red dwarfs make up roughly 3/4 of all the stars in the galaxy. They are small. The smallest red dwarfs are only about 8% of the sun's mass, barely large enough to sustain nuclear fusion at all. They are cool. Their surfaces glow a deep reddish orange rather than the warm yellow-white of the sun. And they are extraordinarily long-lived. A red dwarf with half the mass of our sun can burn steadily for 80 to 100 billion years. The universe is only 13.8 billion years old. No red dwarf that has ever formed has yet had time to die of old age. Every red dwarf that has ever ignited is still burning. All of them. Every single one, still quietly fusing hydrogen in the dark, having barely begun their unimaginably long lives. The smallest red dwarfs, those with only about 1/10 the mass of the sun, may burn for up to 10 trillion years. 10 trillion years. By the time the last of these quiet little stars finally exhausts its fuel, the universe will be nearly 1,000 times its current age. Everything we see around us, every galaxy, every nebula, every structure in the cosmos will have long since changed beyond recognition. And still, those small, patient red stars will be burning. Now let us follow a star like our sun toward the end of its life. Roughly 5 billion years from now, the sun will have consumed most of the hydrogen in its core. The core, now rich in helium, will no longer be producing fusion energy, and without that outward pressure, gravity will begin to win its long argument. The core will contract and heat up, but the rising temperature will cause hydrogen in a shell surrounding the core to begin fusing, and the energy from that shell burning will cause the sun's outer layers to expand enormously. The sun will become a red giant. It will expand to perhaps 200 times its current diameter, large enough that its surface will extend beyond the orbit of Venus, and possibly beyond the orbit of Earth itself. The Earth, if it still exists, will either be engulfed entirely or scorched beyond any recognition of the world we know. The oceans will have evaporated billions of years before that point, but the expansion itself will be the final transformation of the familiar sun. This is not a cause for alarm. It is simply the next chapter. The sun doing what stars do, slowly and without urgency, following the path that gravity and physics have always laid out for it. Eventually, the sun's red giant phase will come to its own quiet ending. The outer layers of the expanded star, loosely held by gravity now that the star has swelled so large, will be gently blown away by a slow stellar wind. Layer by layer, over perhaps 100,000 years, the sun's outer atmosphere will drift outward into the surrounding space, forming a glowing shell of expelled gas called a planetary nebula. The name is slightly misleading. Planetary nebulae have nothing to do with planets. They were named by early astronomers who observed them through small telescopes and thought their round, glowing shapes resembled the disks of planets. What they actually are is one of the most beautiful types of objects in the night sky. Glowing rings and shells of gas, illuminated by the hot stellar remnant at their center. Some are nearly perfectly circular, some are elongated like glowing hourglasses. Some are complex and asymmetric, shaped by stellar winds and the influence of a companion star into fantastic, lacy structures. Each one is a star's last gift to the galaxy. Its outer layers, enriched with the carbon and nitrogen and oxygen produced by nuclear fusion over its lifetime, scattered gently back into the interstellar medium, into the gas clouds from which future stars will form. The stuff of this dying star becoming the stuff of new stars and new planets, and in time, perhaps new living things. At the center of the planetary nebula, what remains of the sun's core will be exposed. A white dwarf, roughly the size of the Earth, but containing perhaps half the original mass of the sun. Enormously dense. A teaspoon of white dwarf material would weigh approximately 5 tons on Earth's surface, but no longer producing energy through nuclear fusion, just radiating the heat it accumulated over its long life, slowly, patiently, into the surrounding dark. A white dwarf cools over billions of years, very slowly, fading from a brilliant blue-white through pale yellow, and then dim orange as the centuries pass. Eventually, in a time so far in the future that the universe will barely resemble anything we know, it will cool enough to become a black dwarf, a cold, dark, inert sphere, no longer glowing at all. The final, quiet, resting state of a star like our sun. No black dwarf has ever yet formed. The universe is not old enough. Every white dwarf that exists is still warm, still fading, still carrying the residual heat of its long stellar life. For the most massive stars, the story ends very differently. A star 10 or more times the mass of the sun does not end in a gentle planetary nebula and a quietly cooling white dwarf. It burns through its fuel recklessly and fast, living for only a few million years. It fuses not only hydrogen, but helium oxygen, neon, silicon, each element in turn as the core grows hotter and denser, building up layer upon layer of heavier elements in its core, like the layers of an onion, until it reaches iron. Iron is the endpoint of stellar nucleosynthesis. Fusing iron does not release energy, it absorbs it. When an iron core builds up at the center of a massive star, fusion can no longer provide outward pressure, and gravity, patient and implacable, wins the argument in a fraction of a second. The core collapses catastrophically. In less than a second, the core goes from the size of the Earth to a sphere roughly 20 kilometers across. The collapse releases an extraordinary burst of energy, and the outer layers of the star, falling inward and then rebounding from the suddenly rigid core, explode outward in a supernova. In those few moments, the dying star releases more energy than the sun will release across its entire 10 billion year lifetime. The supernova can outshine an entire galaxy for weeks, and it scatters the heavy elements from the star's core, the iron and nickel and gold and uranium, across the surrounding interstellar medium, into the gas clouds from which future stars and future worlds will form. The iron in your blood was forged in the core of a star that exploded before our sun existed. What remains after the supernova depends on how much mass was in the original star's core. For some, a neutron star, a sphere only about 20 kilometers across, containing 1 to 2 solar masses of material, so dense that a single teaspoon would weigh billions of tons, made almost entirely of neutrons, packed together as tightly as the nucleus of an atom. Some neutron stars spin hundreds of times per second, sweeping beams of radio waves across the sky like cosmic lighthouses. We call these pulsars. For the most massive stellar cores, not even neutron degeneracy pressure can hold. Gravity wins completely, and the result is a stellar mass black hole, an object so dense that not even light can escape, The galaxy is thought to contain hundreds of millions of them, drifting invisibly through the disk and the halo. The quiet, dark remnants of the most massive stars that ever burned. Dust to dust, gas to gas. Every atom in every star has been part of the cycle, drawn from a gas cloud, fused in a stellar core, scattered back into the medium by a stellar wind or a supernova, gathered again into a new cloud, and eventually drawn into a new star. The galaxy recycles everything. It wastes nothing. Every ending is the beginning of something else. Every dying star enriches the gas that will build the next generation. Every supernova seeds the interstellar medium with the elements that will one day be oceans and mountains. And perhaps, somewhere, the quiet weight of a resting body in the dark. You are made of star stuff, not as a metaphor, as a literal physical fact. The atoms in your body were forged in stellar cores and scattered by stellar winds and supernovae across the galaxy over billions of years before finding their way here. You are the galaxy resting. Let that thought be a warm one. Let it settle around you slowly. You are part of the great cycle. You have always been. And right now, you are the part of it that is at rest. Between the stars, there is something, not nothing, not the pure, perfect vacuum that the word space might suggest, but something, a thin, diffuse, extraordinary mixture of gas and dust and light and magnetic fields and cosmic rays, filling the seemingly empty spaces between every star in the galaxy, filling the spiral arms and the gaps between them, threading through the disk and drifting up into the halo, present everywhere, even in the most apparently empty regions of the Milky Way. There is always something there. We call it the interstellar medium. It is not glamorous in the way that nebulae and supernovae and black holes are glamorous. It does not blaze with dramatic color or emit fierce radiation. Most of it is invisible. Most of it is colder than anything on Earth, or hotter than anything our atmosphere could survive. It is the quiet connective tissue of the galaxy, the substance between things, the medium through which everything moves, and from which everything is ultimately made. Let us drift through it tonight, slowly, letting its textures and its temperatures and its extraordinary variety settle gently into the mind. By mass, the interstellar medium of the Milky Way is approximately 99% gas and 1% dust. Of the gas, roughly 90% is hydrogen in one form or another, and 9% is helium. The remaining fraction of a percent is made of heavier elements, the oxygen and carbon and nitrogen and silicon and iron that earlier generations of stars forged and scattered. These heavier elements are trace quantities, precious, rare, the hard-won products of billions of years of stellar nucleosynthesis, slowly enriching the gas of the galaxy with each new generation of stars. The gas of the interstellar medium exists in several distinct phases, each with its own temperature, its own density, its own particular character. Moving from coldest to hottest is like moving through a sequence of almost unimaginably different environments, all of them coexisting within the same galaxy, often within the same region of the disk. The coldest phase is the molecular gas. We have already visited the great molecular clouds where new stars are born. But molecular gas exists in smaller concentrations too, in cold, dense clumps scattered through the disk. The temperature in these regions ranges from about 10 to 30 degrees above absolute zero. At these temperatures, atoms bond together into molecules. Hydrogen pairs into molecular hydrogen. Carbon and oxygen combine into carbon monoxide. Water forms. Ammonia forms. Long organic chains assemble quietly in the dark, driven by nothing more than chemistry and the faint energy of passing starlight. Over 100 different molecules have been identified in interstellar molecular gas. Some of them are genuinely surprising in their complexity. Glycolaldehyde, a simple sugar, ethyl formate, the molecule partly responsible for the scent of raspberries. Amino acids, the building blocks of proteins, have been detected in meteorites that formed from the same molecular cloud material as our solar system. The interstellar medium is not sterile. It is chemically active, quietly, patiently building complex molecules in the cold and dark between the stars. A little warmer, and we enter the cold, neutral medium. Here, temperatures range from about 10 to 100 degrees above absolute zero. The gas is mostly atomic hydrogen, not yet bonded into molecules, too warm for molecular chemistry, but too cold to be ionized. These are the cool hydrogen clouds that drift through the disk of the galaxy, detected by radio telescopes through the faint signal of a very particular phenomenon. The hydrogen atom has a nucleus, a single proton, and a single electron. Both the proton and the electron have a property called spin. And when the spin of the electron flips from aligned with the proton to opposed, the atom releases a tiny amount of energy as a photon of radio waves at a very specific wavelength, 21 centimeters. The 21 centimeter line. It is one of the most important signals in all of radio astronomy, because hydrogen is so abundant and so widespread, and because radio waves pass through the dust and gas of the galaxy with very little absorption. The 21 centimeter line allows astronomers to map the hydrogen gas across the entire disk of the Milky Way, to trace the spiral arms, to measure the rotation of the galaxy, to chart the distribution of cold, neutral gas from one side of the disk to the other, all from a single, quiet, faint radio signal produced by hydrogen atoms flipping their electron spins in the dark. Warmer still, and we enter the warm, neutral medium. At temperatures between about 6,000 and 10,000 degrees Kelvin, hydrogen gas exists in its neutral atomic form, but is much more energetic than the cold, neutral medium. This warm, neutral gas fills a significant fraction of the volume of the galactic disk. It is still thin, extraordinarily thin by earthly standards. The density of warm neutral gas is typically only about half an atom per cubic centimeter in a cubic centimeter of the air around you right now. There are roughly 27 million trillion molecules. In a cubic centimeter of warm, neutral interstellar medium, there are fewer than one atom. And yet, across the vast distances of the galaxy, even this near emptiness adds up to an enormous reservoir of mass. Near hot young stars, the interstellar medium is transformed. The intense ultraviolet radiation pouring from massive young stars is energetic enough to strip electrons from hydrogen atoms, ionizing them. In the regions immediately surrounding these hot stars, the gas is fully ionized, consisting of free protons and free electrons, glowing with the characteristic red light of hydrogen recombination. These are the HII regions, the glowing emission nebulae we visited in section 11. The great pillars and arches of the Eagle and Carina nebulae, the luminous heart of the Orion Nebula. HII regions are among the most visually spectacular objects in the galaxy, but they occupy only a tiny fraction of the total volume of interstellar space. They are bright oases in a much vaster, dimmer landscape. And then there is the hot, ionized medium, the hottest phase of the interstellar medium, produced by the shock waves of supernova explosions. When a massive star explodes, it drives a blast wave outward through the surrounding gas at speeds of thousands of kilometers per second. That blast wave heats the gas it encounters to temperatures of millions of degrees. At such temperatures, the gas is fully ionized and extremely tenuous, so hot that it emits not visible light, not radio waves, but X-rays. The hot ionized medium glows in X-rays, detectable only by space-based observatories above the Earth's atmosphere. The hot ionized medium fills perhaps half of the total volume of the galactic disk. All that seemingly empty space between the gas clouds, threaded with the remnants of ancient supernova shock waves, glowing at millions of degrees, too thin to feel, but too energetic to ignore. Now let us turn to the dust. Interstellar dust makes up only about 1% of the mass of the interstellar medium. But that 1% has an effect on the galaxy that is completely disproportionate to its weight. Interstellar dust grains are not the soft, fluffy particles that settle on shelves and windowsills. They are tiny. Most are between 1/10 of a micron and a few microns across, smaller than the wavelength of visible light, made mostly of carbon in the form of graphite or amorphous carbon, and silicon compounds coated in the coldest regions with thin mantles of ice. Water ice, methanol ice, carbon dioxide ice. These tiny grains absorb and scatter starlight. Shorter wavelengths of light, the blue end of the spectrum, are scattered more strongly than longer wavelengths. This is why stars seen through a veil of interstellar dust appear redder than they actually are. The blue light is scattered away. The red light passes through more easily. The same physics that makes sunsets red on Earth operates across the entire disk of the Milky Way, reddening the light of distant stars, making the galaxy's inner regions look warmer and more amber than they truly are. This effect is called interstellar reddening, and correcting for it is one of the ongoing practical challenges of observational astronomy. Dust is also a surface for chemistry. In the cold regions of the interstellar medium, the surfaces of dust grains act as tiny platforms where atoms can meet and bond. Hydrogen atoms drifting through the gas encounter a grain, stick briefly to its surface, encounter another hydrogen atom, and bond together to form molecular hydrogen. Two hydrogen atoms that would never have met in the open gas find each other on the surface of a grain the size of a bacterium, drifting in the dark between the stars. Without dust grains, the molecular clouds could not exist. Without molecular clouds, stars could not form. Without stars, there would be no planets, no light, no warmth, no life. The galaxy's living complexity ultimately rests, in part, on the availability of these tiny, unremarkable specks of carbon and silicon, drifting invisibly through the interstellar medium, doing their quiet chemical work in the cold and the dark. There is also the cosmic ray component of the interstellar medium. Cosmic rays are not rays in the usual sense. They are fast-moving particles, mostly protons and atomic nuclei, accelerated to nearly the speed of light by supernova shock waves and other violent events in the galaxy. They travel through the interstellar medium in all directions, bouncing off magnetic field lines, spiraling through the disk and the halo, occasionally colliding with the nuclei of gas atoms and producing secondary particles. Cosmic rays are everywhere in the galaxy. They pass through you right now, just as dark matter does, just as neutrinos do. One or two cosmic ray particles pass through every square centimeter of your body every minute. They have done so for every minute of your life. They are part of the background of the cosmos itself, as universal and as invisible as the microwave background radiation left over from the Big Bang. The interstellar medium breathes, not quickly, not on any timescale a human life could perceive, but it cycles. Gas is drawn into molecular clouds and collapsed into stars. Stars fuse that gas and scatter it back, enriched through stellar winds and supernovae. The returned gas mixes with the remaining interstellar medium, enriching it with heavier elements. Future generations of stars form from this enriched gas. Their planets are more complex. Their potential for chemistry is greater. Each cycle of the interstellar medium is the galaxy slowly building toward greater complexity, slowly enriching itself, slowly producing the conditions for more intricate chemistry, more diverse worlds, more elaborate structures. The galaxy between the stars is not empty. It is the medium of everything, the slow, patient, invisible breath of the Milky Way, drifting, cycling, building. Let it drift through your mind now like something weightless, like the faintest trace of a cloud. Let it be light and quiet and easy, the medium between things, the substance of the spaces, the breath between the stars. You are breathing too, slowly, easily, in the quiet. Our galaxy does not travel alone. Orbiting the Milky Way, the way moons orbit a planet, is a family of smaller galaxies. Some of them are visible to the naked eye. Some are so faint and diffuse that they were only discovered within the last few decades, as our telescopes grew powerful enough to pick out the faintest gatherings of stars against the deep dark of the surrounding sky. These are the satellite galaxies, the companions of the Milky Way. They range enormously in size and brightness from the large Magellanic Cloud, a galaxy so large that it contains perhaps 30 billion stars, and would be classified as a significant galaxy in its own right if it were not so close to ours, down to the ultra-faint dwarfs, tiny wisps of a few thousand stars, so dim and so spread out that they are barely distinguishable from the random scatter of halo stars around them. As recently as the early 2000s, astronomers knew of only about 11 satellite galaxies orbiting the Milky Way. Today, with modern surveys and more sensitive instruments, that number has grown to more than 60 confirmed companions, with more being discovered regularly. Each new survey of the sky reveals yet another faint, ancient companion drifting in its slow orbit around our galaxy. Let us visit the most prominent of these companions tonight. To visit the Magellanic Clouds, we must first turn our attention to the southern sky. From the northern hemisphere, neither of the Magellanic Clouds is visible. But from the southern hemisphere, on a clear, dark night far from city lights, they appear unmistakably two soft patches of light, larger and brighter than any other object in the sky, except the moon itself and the band of the Milky Way. They look like detached pieces of the Milky Way, broken free and drifting independently in the southern sky, which, in a sense, is almost what they are. Sailors and navigators of the southern hemisphere have known these objects for thousands of years. Indigenous Australians, Polynesian navigators, the peoples of southern Africa and South America all had their own names and stories for the two bright clouds in the southern dark. The name Magellanic Cloud was given to them by European sailors in the 16th century, after the explorer Ferdinand Magellan, whose expedition circumnavigated the Earth between 1519 and 1522. Magellan's crew wrote detailed descriptions of the two glowing patches, and European astronomers subsequently named them in his honor. But these clouds had been watched and named and woven into stories long before any European sailor ever sailed south far enough to see them. The large Magellanic Cloud lies approximately 160,000 light years from Earth. 160,000 light years. Close enough that individual stars within it can be resolved through a modest telescope. Close enough that when a massive star within it exploded as a supernova in 1987, the light and neutrinos from that explosion reached Earth and were detected by observatories around the world. That event, called SN 1987A, was the first naked-eye supernova since the year 1604, and remains one of the most studied astronomical events in history. The light from the death of a star 160,000 light years away, visible on a clear night without any telescope at all. The large Magellanic Cloud is a dwarf irregular galaxy, its shape distorted and asymmetric, shaped over billions of years by the gravitational tug of the Milky Way and by its close interactions with its smaller companion. It contains roughly 30 billion stars spread across a region about 14,000 light years wide. It is actively forming new stars. Its star-forming regions are some of the most vigorous in the entire local group of galaxies, the Tarantula Nebula, a massive star-forming region within the large Magellanic Cloud, is so large and so luminous that if it were as close to us as the Orion Nebula, it would cast shadows on the ground at night. The most massive known star in the universe, a giant called R136 Aeon, with a mass approximately 265 times that of our Sun, lives within the Tarantula Nebula, a star so extreme that it is barely stable, shedding mass continuously in fierce stellar winds, burning with a luminosity millions of times greater than the Sun. A brief, brilliant, almost impossibly intense life. The small Magellanic Cloud lies a little further away, about 200,000 light years from Earth. It contains perhaps several 100 million to a few billion stars, spread across a region about 7,000 light years wide. Like its larger companion, it is irregular in shape, without the clean spiral arms or the settled spherical structure of older, more established galaxies. It is a galaxy still being shaped, still responding to the forces around it. The small Magellanic Cloud was once probably a barred spiral galaxy. Astronomers can trace a faint central bar structure within it even now. But billions of years of gravitational interaction with both the Milky Way and the large Magellanic Cloud have disrupted and distorted it, pulling it out of its original form into the irregular, somewhat ragged shape it has today. Connecting the large and small Magellanic Clouds is a bridge of gas and stars called the Magellanic Bridge. It stretches between the two galaxies across approximately 75,000 light years of space, a testimony to the gravitational interaction between them. The two clouds collided with each other approximately 300 million years ago. The collision stripped gas and stars from the small cloud and flung them across the bridge toward the large cloud. New stars are forming within the Magellanic Bridge even now, born in the stream of gas between two galaxies. Stars forming not inside any galaxy, but in the space between them. behind the Magellanic Clouds as they orbit the Milky Way is one of the most remarkable structures in the local group. The Magellanic Stream, a long, thin arc of gas stretching for more than 150 degrees across the sky, following the orbital path of the Magellanic Clouds like the tail of a slow, enormous comet. The stream is made of neutral hydrogen gas, stripped from the Magellanic Clouds over billions of years by the combined gravitational and ram pressure forces of their passage through the Milky Way's hot gaseous halo. The Magellanic Stream contains no stars, only gas, a river of raw material flowing slowly along the orbit of the clouds, gradually being drawn toward the Milky Way. Astronomers estimate that over the next several billion years, this gas will eventually fall into the Milky Way and fuel new generations of star formation. The satellite galaxies feeding their larger host, giving of themselves slowly over eons to enrich the galaxy they orbit. Beyond the Magellanic Clouds, the family of satellite galaxies becomes smaller and dimmer. There are the classical dwarf spheroidal galaxies, Sculptor, Fornax, Carina, Sextans, Leo II, each one a small, rounded, diffuse collection of ancient stars, containing anywhere from a few 100,000 to a few tens of millions of stars, orbiting the Milky Way at distances ranging from a few tens of thousands to several 100,000 light years. These dwarf spheroidals are extraordinary objects in their own right. They are among the most dark matter dominated objects known in the universe. Some of them contain up to 1,000 times as much dark matter as visible matter. The ratio of invisible mass to visible mass in these tiny galaxies is far higher than in large galaxies like the Milky Way. They are, in a sense, dark matter halos with just the faintest dusting of stars, enormous dark structures made visible only by a handful of ancient suns drifting within them. And then there are the ultra-faint dwarfs. These are the smallest, dimmest, most sparse galaxies known. Some of them contain only a few thousand stars. Objects like Segway 1, Segway 2, Willman 1, and the recently discovered Aquarius III and Leo VI, announced in early 2025. These tiny gatherings of ancient metal-poor stars are almost invisible against the background sky, detectable only through careful statistical analysis of deep survey images, looking for slight excesses of old stars concentrated in a small area of sky. They are the faintest galaxies known, and yet they are still galaxies, still self-gravitating systems, still ancient collections of stars following their own slow orbits within the larger embrace of the Milky Way's dark matter halo, still carrying within them some of the oldest stars in the universe, metal-poor and ancient, formed in the very earliest epoch of galaxy formation. The Milky Way is slowly consuming its satellite galaxies, not rapidly, not violently, just slowly over billions of years. The gravitational tides of the Milky Way pull at each satellite as it passes through the inner regions of the halo, stretching it, drawing stars away from it, scattering them into long tidal streams in the halo. Each close passage erodes the satellite a little more, until eventually what remains may be too small and too diffuse to hold together at all, and the satellite dissolves entirely into the Milky Way's growing halo. This is the Milky Way growing, feeding, becoming very slowly, slightly larger and slightly more massive with each satellite it absorbs. The same process that built the halo over billions of years continues today, quietly, in the outer reaches of the galaxy. But right now, the Magellanic Clouds are still there, still visible from the southern sky on a clear night as two soft, pale patches of light, still orbiting, still intact, still sending their slow river of gas trailing behind them through the dark. Two companions in the southern sky, patient and luminous and close on a galactic scale, making their long, slow orbit around our galaxy as they have been doing for billions of years. Let the image of those two soft lights settle gently in your mind. The southern sky, the warm dark, two small galaxies drifting in faithful orbit, everything moving, everything patient, everything held together by the quiet, tireless force of gravity. You are resting. The companions drift on. The Magellanic Stream trails its slow arc across the sky, and the galaxy turns, as it always has, carrying all its companions and all its stars and all its ancient dark matter and all its drifting gas in one great, slow, unhurried motion through the night. There is a galaxy passing through ours right now, not approaching from a distance, not something that will happen in the far future. Right now, at this very moment, a small dwarf galaxy is moving through the disk of the Milky Way. Its stars are mingling with our stars. Its tidal streams are wrapping around the entire galaxy. And our own solar system may be drifting through the outskirts of its debris trail, even as we rest here tonight. It is called the Sagittarius Dwarf spheroidal galaxy. It is not a dramatic collision. There are no explosions, no visible changes in the night sky, nothing that any human eye has ever noticed or ever will notice directly. Just a slow, gentle, billions of years long merger, a small galaxy being quietly absorbed by a much larger one. Over timescales so vast that the violence, such as it is entirely invisible to us. Let us drift into this story together. It is one of the most intimate and remarkable stories in the history of our galaxy. The Sagittarius Dwarf was discovered only relatively recently, in 1994, by astronomer Rodrigo Ibada and his colleagues at the University of Cambridge. Its late discovery might seem surprising. It is one of the closest galaxies to the Milky Way, currently sitting only about 70,000 light years from the galactic center, on the far side of the galaxy from us, but it was hidden in plain sight for decades. Its stars are scattered across a large area of sky, diluted by the overwhelming number of Milky Way stars in the same direction. and it lies almost directly behind the galactic center, in the direction of Sagittarius, where the dust and gas of the galaxy's disk obscure observations in visible light. When astronomers finally identified it, mapping the velocities of stars in that region and finding a coherent group moving together against the background of Milky Way stars, they discovered something extraordinary. This was not a distant, separate object. It was right here, practically on our doorstep, and it was being torn apart. The Sagittarius Dwarf is in a polar orbit around the Milky Way. While most of the Milky Way's stars orbit in the flat plane of the disk, the Sagittarius Dwarf travels in a steeply inclined path, looping over the galaxy's north pole, and under its south pole, threading through the disk twice. With each orbit, its orbital period is roughly 1 billion years, and it has been making these passages, these slow transits through the disk of the Milky Way, for billions of years. Each passage costs the Sagittarius Dwarf something. As it passes through the dense disk, the tidal forces of the Milky Way pull at it from all sides. Stars at the near edge of the galaxy, closer to the Milky Way's center, feel a stronger gravitational pull than stars at the far edge. This difference in pull stretches the dwarf galaxy, draws stars away from it, flings them into long, curving streams that follow the orbit of the parent galaxy, trailing ahead of and behind it like the slow wake of a boat moving through still water. Over billions of years, these stripped stars have spread into what astronomers call the Sagittarius Stream, a vast, loop-shaped river of stars wrapped almost entirely around the Milky Way, stretching in some directions to distances of more than 1 million light years from the galactic center. One of the largest structures visible in the local group. The Sagittarius Stream was mapped in detail using data from the 2-micron all-sky survey, and later from the extraordinary precision of the European Space Agency's Gaia satellite. Gaia, launched in 2013, has been measuring the positions and velocities of more than 1 billion stars in the Milky Way with extraordinary precision. And within that vast catalog of stellar motions, the stars of the Sagittarius stream appear clearly, moving together, sharing the same orbital direction, the same chemical composition, the unmistakable signature of stars that once belonged to the same small galaxy and are now dispersed into the halo of their captor. The stream wraps around the galaxy in multiple loops, leading arms of stars that were pulled away from the front of the dwarf galaxy as it fell inward. Trailing arms of stars drawn from behind, some parts of the stream pass relatively close to our own solar system. We are, according to some calculations, presently drifting within or very near the outer edges of the Sagittarius stream's debris. Some of the stars in our local neighborhood, moving at unusual velocities or with unusual chemical compositions, may be former members of the Sagittarius Dwarf galaxy, immigrants captured long ago by the Milky Way's gravity and now blended almost indistinguishably into its halo. The Sagittarius Dwarf has already lost an enormous fraction of itself. When it first fell toward the Milky Way, perhaps 8 to 10 billion years ago, it is estimated to have had a mass of approximately 10 billion solar masses. Roughly 1% of the Milky Way's total mass, a modest but not insignificant dwarf galaxy, probably containing several 100 million stars and a large dark matter halo. Today, the bound remnant of the Sagittarius Dwarf, the core that has not yet been dispersed into streams, contains only a few tens of millions of stars. It has lost roughly 1/3 of its stars, and perhaps 9/10 of its dark matter. The dark matter that once formed its halo has been stripped away and merged into the Milky Way's own dark matter halo over billions of years of interaction. The galaxy is growing in part by absorbing the Sagittarius Dwarf, gaining its stars, gaining its dark matter, being subtly reshaped by each encounter. And this is one of the most remarkable discoveries of recent years. the passages of the Sagittarius Dwarf through the Milky Way's disk have not been quiet events for our galaxy. They have left their mark on us. In 2020, a team of astronomers using data from the Gaia satellite found evidence of 3 distinct episodes of increased star formation in the Milky Way's history, occurring approximately 5.7 billion years ago, 1.9 billion years ago, and 1 billion years ago. These 3 peaks of star formation coincide almost precisely with the 3 known passages of the Sagittarius Dwarf through the galactic disk. When the Sagittarius Dwarf passed through the disk, its gravitational influence disturbed the gas and dust of the Milky Way. The disturbance was like dropping a stone into still water. Ripples spread outward from the impact site. In some regions, the ripples compressed the gas, creating higher densities that triggered the collapse of molecular clouds into new stars. In other regions, the gas was dispersed, leaving emptier zones. The entire disk of the Milky Way sloshed gently, like water in a slowly stirred bowl. And from one of those episodes of triggered star formation, approximately 4.7 billion years ago, our own solar system may have been born. The Sagittarius Dwarf may have helped create our sun. Its gravitational ripples may have reached the particular molecular cloud from which the sun and Earth and all the planets formed, may have nudged that cloud into collapse just a little sooner than it would otherwise have begun, may have set in motion the sequence of events that led, 4.5 billion years later, to you lying here, resting, listening to these words. It is a connection so indirect, so stretched across billions of years and tens of thousands of light years, that it seems almost too tenuous to hold. And yet the physics is real. The timing matches. The evidence is there in the Gaia data. The small galaxy on the far side of the Milky Way, following its slow polar orbit, may have had a hand in our very existence. Supercomputer simulations of the Sagittarius Dwarf's impact on the Milky Way have revealed something else. something unexpected and beautiful. The simulations suggest that the repeated impacts of the Sagittarius Dwarf, particularly the gravitational influence of its dark matter halo, may have helped shape and maintain the Milky Way's spiral arms. Without those perturbations, the spiral structure of the Milky Way might have faded and dissipated over time. The disk might have settled into a more uniform, less structured form, but the repeated passages of the Sagittarius Dwarf, each one sending gravitational ripples through the disk, kept the spiral pattern stirred and active. The spiral arms we live beside, the great winding structures we explored in the early sections of this journey, may owe something of their shape and persistence to the small galaxy that has been slowly falling into ours for billions of years. The remnant core of the Sagittarius Dwarf is currently moving toward another passage through the galactic disk. It is expected to pass through within the next 100 million years or so. A short time in cosmic terms, and each passage will leave it smaller, more dispersed, more thoroughly woven into the fabric of the Milky Way. Within perhaps 1 billion years, the remaining bound core of the Sagittarius Dwarf will have dispersed entirely. Its last stars will scatter into the halo. The galaxy will be gone as a distinct object, absorbed, merged, become part of the Milky Way, indistinguishably. A small galaxy, patient and ancient, slowly giving itself over to the larger one, its stars becoming our stars, its dark matter becoming our dark matter, its ancient chemical signature woven into the halo, detectable for billions of years, yet by the careful measurements of telescopes that do not yet exist. There is something very quiet and very tender in this story. A small galaxy falling toward a large one, not fighting it, not escaping it, just following the path that gravity laid out, making its slow orbits, offering up its stars one passage at a time, being absorbed gently over billions of years into something vastly larger than itself. And in the process, perhaps seeding the star formation that created our sun, perhaps shaping the spiral arms that define the structure of our galaxy, perhaps scattering a few of its own ancient stars into our local neighborhood, where they drift now among the familiar stars of the halo, quiet and metal poor and old, carrying in their chemistry the memory of a galaxy that no longer quite exists. Let that settle gently into your mind. The slow merger, the ancient orbit, the small galaxy giving itself over patiently and completely to the pull of something larger. There is a rest in that image, a letting go, a slow release. You are resting too, letting go, being held by something larger than yourself, warm and still and carried. You are moving right now, not in any way you can feel, not in any way that disturbs the warmth of the room or the stillness of your body. But you are moving. Everything around you is moving, and the scale of that motion is extraordinary. The Earth is spinning on its axis, carrying you around at roughly 1,600 kilometers per hour if you live near the equator. The Earth is orbiting the Sun, carrying you along at about 107,000 kilometers per hour. And the Sun, carrying the entire solar system, every planet and moon and comet and asteroid, and the thin, warm breath of the heliosphere, is orbiting the center of the Milky Way at approximately 828,000 kilometers per hour. 828,000 kilometers per hour. In 90 seconds, everything you know moves 20,000 kilometers through the galaxy. And yet you are perfectly still, warm and resting in the dark, feeling nothing of this extraordinary motion, because all of it, every revolution and every orbit, is so smooth and so constant that there is no sensation of movement at all, just the feeling of being at rest, which you are in the deepest sense, while simultaneously hurtling through the cosmos at speeds no human vehicle has ever approached. Let us ride this journey together for a while, quietly, without needing to do anything at all. The Sun has been orbiting the galactic center for almost its entire existence. Since it formed approximately 4.6 billion years ago from the collapse of a molecular cloud in the Orion Arm, it has been tracing its great looping path around the galaxy, and in that time, it has completed approximately 20 full orbits, 20 galactic years. A single galactic year, sometimes called a cosmic year, is approximately 225 to 230 million Earth years. The time for the solar system to complete one full circuit around the galactic center. 20 of those journeys have brought us to the place we are now. The particular position in the galaxy, the particular orientation in space, the particular moment in cosmic time that we occupy tonight. One galactic year ago, the last of the non-avian dinosaurs had only recently disappeared from Earth. The age of mammals was just beginning. Horses were the size of cats. Whales were small, four-legged creatures just beginning to return to the sea. And the solar system was in an entirely different part of its orbit around the galaxy, a different position in the spiral arm, a different configuration with respect to the surrounding stars. 2 galactic years ago, the first dinosaurs were only just appearing. The great Permian extinction had recently wiped out the majority of life on Earth, and evolution was slowly, tentatively filling the empty ecological niches with new forms. 3 galactic years ago, complex multicellular life had barely appeared on Earth at all. The oceans were full of simple organisms. No creature had yet evolved to walk on land. The galaxy has served as the slowest of clocks, counting out these vast intervals, while life on Earth made its long and improbable journey. Our orbit around the galactic center is not perfectly circular. It is slightly elliptical, carrying the solar system a little closer to the galactic center, and then a little further away as the orbit proceeds. At its closest, the Sun approaches to perhaps 24,000 light years from the center, At its furthest, it reaches perhaps 28,000 light years. The average distance is approximately 26,000 light years. This gentle variation in distance is one reason astronomers describe our location as middle, not locked at a fixed distance, but moving within a moderate range, staying within that habitable zone of the galaxy, neither too close to the dangerous center, nor too far into the sparse, heavy element poor outer regions. But the solar system's journey around the galaxy is not simply a flat, circular path. There is a vertical motion too, a slow, gentle bobbing above and below the plane of the galactic disk. The disk of the Milky Way is not a rigid, perfectly flat structure. It has gravity, and that gravity tends to pull objects back toward the midplane. As the solar system orbits the galactic center, it oscillates, rising above the disk, being pulled back down, crossing through the midplane, continuing below the disk, being pulled back up, crossing through again. The period of this oscillation is approximately 64 million years, from one crossing to the next crossing, or roughly 32 million years from the midplane to the highest or lowest point of the excursion. At its most extreme, the solar system travels perhaps 200 to 300 light years above or below the plane of the disk before gravity pulls it back. Right now, the solar system is currently north of the galactic midplane, above it by roughly 50 to 80 light years, and moving further above it still. We are in the gentle upswing of one of these slow oscillations, drifting slowly away from the densest part of the disk, moving toward a high point we will reach tens of millions of years from now, before beginning our slow descent back down toward the midplane. It is an ancient, pendulum-like motion, and like a pendulum without friction, it never stops. It simply swings back and forth through the disk, above and below, over and over in the same patient rhythm for as long as the galaxy holds together. As the solar system bobs through the disk, it periodically passes through denser regions of the interstellar medium. These passages change the environment of the solar system slightly. When we are within a denser gas cloud, the boundary of the heliosphere, the bubble of solar wind that surrounds the solar system and shields it from interstellar particles, may be compressed. The amount of interstellar material entering the inner solar system may increase. These environmental changes, subtle as they are, may have influenced the climate of the Earth over geological timescales. Some researchers have proposed connections between the solar systems, passages through the galactic disk, and patterns in the long-term climate record of Earth. Though these connections remain a subject of ongoing research, the galaxy and the Earth are not entirely separate systems. The Earth's history has been shaped in ways both direct and subtle by the larger galactic environment through which the solar system travels. There is another way in which the solar system's galactic journey has shaped our world. As we orbit the galactic center, we move in and out of regions of different stellar density. Sometimes we pass relatively close to other star systems, not close enough for any dramatic gravitational interaction in most cases, but close enough, perhaps, to perturb the distant Oort cloud that surrounds our solar system. The Oort cloud is a vast, spherical shell of comets and icy bodies, extending perhaps a quarter of the way to the nearest star. It is the most distant region of the solar system, the remnant of the original solar nebula's outer edges, and it is only very loosely bound to the sun. A passing star, or even the tidal force of the galactic disk itself, can disturb the orbits of Oort cloud bodies and send them falling inward toward the sun and the inner planets. Some of the great long-period comets that have lit up Earth's skies over the centuries, those slow, brilliant visitors from the outer darkness with their long, glowing tails, began their journeys when the gentle tide of the galaxy nudged them from the Oort cloud, the galaxy reaching into our solar system, sending us these brief, icy messengers from the cold outer dark. sometimes it is worth simply sitting with the numbers of our journey, not to understand them fully, but just to let them wash through the mind like a slow tide. In the time it takes you to draw one slow breath tonight, the solar system has traveled approximately 23 kilometers through the galaxy. In one full night of sleep, perhaps 8 hours, the solar system has moved roughly 660,000 kilometers along its galactic orbit. In a human lifetime of 80 years, the solar system moves approximately 5,800 billion kilometers, a distance that light would take nearly 600 years to cross. And yet, in galactic terms, a human lifetime barely registers. In 80 years, the solar system completes roughly 3/10,000,000ths of one galactic orbit, a fraction so small it barely has a name. You are, in the grandest possible sense, almost perfectly still. There is a word for what we are experiencing right now. If we allow ourselves to think about it in this way, the word is carried. You are being carried by the earth in its daily spin and its yearly orbit, by the solar system in its great 225 million year journey around the galactic center, by the Milky Way itself, which moves through the local group of galaxies, which drifts through the larger Virgo supercluster, which is itself drawn toward the great attractor at the heart of the Laniakea supercluster, layer upon layer of motion, each one larger and slower than the last, all of them operating simultaneously and continuously, carrying you across the cosmos while you lie perfectly still. You do not need to do anything to be on this journey. You are already on it. You have been on it since the moment you were born. The galaxy is carrying you. It has always been carrying you, and tonight it carries you gently through the dark, along the arc of its long, slow orbit at 828,000 kilometers per hour. And you are resting, still and warm, carried, moving without moving, traveling without effort, part of the great orbital dance of the cosmos, resting in the dark while everything turns. On a clear autumn night, far from any city, in the northern hemisphere, there is a faint smudge of light just visible to the naked eye in the constellation Andromeda. It does not look like much, just a soft, pale oval blur, slightly larger than a star, slightly diffuse at its edges. Easy to miss if you do not know where to look, easy to overlook entirely if the sky is anything less than truly dark. But that faint smudge is the most distant object visible to the naked human eye. It is the Andromeda galaxy, and it is approximately 2.5 million light years away. The light reaching your eyes from that soft glow left its source 2.5 million years ago, when our ancestors were walking the African savanna, and the word galaxy had not yet been invented by any mind on Earth. And it is coming toward us, not quickly by human standards, but steadily, closing the distance between us at roughly 300 kilometers every second, moving toward the Milky Way with the patient, irresistible momentum of something too massive to be stopped by anything in the universe except something equally massive. This is the story of a future that is so far away it will never touch a human life. And yet, it is written in the physics of the present, already determined, already in motion. Let us imagine it together, slowly, gently, without alarm, for this story, however vast, is ultimately a story of transformation rather than destruction, of something ending and something else beginning. The Andromeda galaxy is the largest member of the local group, the small cluster of galaxies, of which the Milky Way is also a member. It is a barred spiral galaxy, broadly similar in structure to our own, though somewhat larger, where the Milky Way contains perhaps 200 to 400 billion stars. Andromeda may contain up to 1 trillion. Its disk stretches across a diameter of roughly 220,000 light years. Its dark matter halo extends even further. By most measures, Andromeda is the heavyweight of the local group, our galaxy's largest and closest major companion. Andromeda has its own history of mergers and absorptions. Astronomers have found evidence that it collided with another large galaxy, roughly the mass of the Milky Way, sometime in the past 2 to 5 billion years. That ancient collision thickened Andromeda's disk, enriched its stellar halo with metal-rich stars, and left a giant stream of debris wrapping around its outer regions. Andromeda arrived at its current state through the same slow process of accretion and merger that has shaped the Milky Way. Both galaxies are the product of billions of years of galactic archaeology. Both are assembled in part from the remains of smaller galaxies they absorbed. And now they are approaching each other. For much of the 20th century, astronomers assumed the Milky Way and Andromeda would definitely collide. The two galaxies are gravitationally bound. Neither is moving fast enough to escape the other's pull. A merger seemed inevitable, but more recent research has added nuance and uncertainty to that picture. In 2024 and 2025, new studies using refined measurements of Andromeda's motion, obtained from the extraordinary precision of the European Space Agency's Gaia satellite, and from advanced computer simulations, found that the outcome is less certain than once thought. A study published in Nature Astronomy in 2025 found that while Andromeda is indeed approaching the Milky Way, the precise sideways component of its motion, the degree to which it is moving past us rather than directly toward us, is uncertain enough that a direct collision within the next 10 billion years happens in only about half of the simulation runs. In others, the two galaxies pass close to each other and then separate, pulled back together only over far longer timescales by the collective gravity of the local group. What seems certain is this: the two galaxies will interact. They will affect each other. And eventually, over timescales of tens of billions of years, all the galaxies of the local group will merge into a single large elliptical galaxy. Whether that process begins with a dramatic direct collision between the Milky Way and Andromeda in 4 to 5 billion years, or proceeds more gradually, the end result is the same. Let us imagine the more dramatic version of events. A direct collision beginning in approximately 4 billion years. The first sign will be subtle. Billions of years from now, the night sky as seen from the Earth, if the Earth still exists in a form that could support an observer, will slowly begin to change. Andromeda, now visible as a faint smudge, will grow imperceptibly brighter over millions of years. Then more noticeably brighter. Then, over hundreds of millions of years, it will begin to resolve. Its spiral arms will become distinguishable. Its central bulge will glow. It will fill more and more of the sky as the two galaxies fall toward each other. At roughly 3.5 to 4 billion years from now, Andromeda will be close enough that its structure will be clearly visible to any naked eye, sprawling across a large portion of the sky. Its tidal forces will begin to reach into the Milky Way's outer disk. Stars in the outer regions of both galaxies will begin to be drawn into long tidal streams, pulled between the two galaxies as the gravitational interaction grows stronger. The first close passage of the two galaxies will be extraordinary to imagine. The two disks will partially overlap. Streams of stars will be flung outward by tidal forces in great arcs. New star formation will be triggered throughout both galaxies as the collision compresses gas clouds and collapses them into new stars. The sky, from any hypothetical vantage point within either galaxy, will be blazing with new starlight. And yet the individual stars will almost certainly not collide. This is the remarkable thing about a galaxy collision. Despite the billions of stars involved, despite the extraordinary scale of the event, the individual stars are so small relative to the distances between them that direct stellar collisions will be extraordinarily rare. The galaxy is mostly empty space. When two galaxies pass through each other, most of the stars simply fly past each other on slightly altered paths, like two swarms of fireflies passing through each other in the dark. If you were on a planet around a star somewhere within the Milky Way during the collision, you would not feel the collision in any physical sense. The sky would change dramatically over millions of years. New stars would appear. The familiar constellations would be unrecognizable. The band of the Milky Way would be replaced by something stranger and more complex. But no catastrophic shockwave would reach you. No wall of fire would sweep through, just a very slow, very vast, very beautiful rearrangement of the sky. After the first close passage, the two galaxies will swing apart briefly, drawn back by their mutual gravity. A second passage, then more interactions, each one drawing the two systems more tightly together. Over roughly 2 billion years of interaction, the two spiral galaxies will gradually lose their individual shapes. The spiral arms will be disrupted and dispersed. The two disk structures, so carefully assembled over billions of years, will blend and mix. Stars originally from Andromeda will find themselves orbiting alongside stars originally from the Milky Way, and neither will know the difference. The two supermassive black holes, Sagittarius A and Andromeda's own central black hole, estimated to be perhaps 100 million solar masses, will spiral toward each other over millions of years after the galaxies merge, drawn together by dynamical friction as they lose energy to the surrounding stellar system. Eventually, they will form a binary black hole. And eventually, over timescales that may be very long, they will merge in a tremendous burst of gravitational waves. The single, larger black hole that results will sit at the center of the merged galaxy. What remains, the merged galaxy, has been playfully named Milkomeda by some astronomers. It will not be a spiral galaxy. It will be a large elliptical galaxy, rounded, smooth, lacking the flat disk and sweeping spiral arms that both of its parent galaxies once possessed. Its stars will orbit in random orientations, not all turning together in the same plane, but distributed in a great sphere, drifting on tilted and elliptical paths. It will be a different kind of beauty, older looking, more settled, the galaxy that forms after the turbulence of collision has passed, and the stars have found their new equilibrium. And what of our sun? Computer simulations suggest that during the merger, the sun has a small but non-zero chance of being ejected from the merged galaxy entirely, flung outward by gravitational interactions into the vast darkness of intergalactic space. More likely, the sun will end up in the outer regions of the merged Milky galaxy, far from the new center, in a quieter, sparser neighborhood than the one it currently occupies. But the sun will not have survived in its current form by then. By the time the Andromeda collision begins in earnest, roughly 4 billion years from now, the sun will be entering its red giant phase, expanding, warming the solar system beyond any possibility of life as we know it. Long before any star in the Milky Way feels the first gravitational tug of the collision, the story of life on Earth, whatever form it may have taken by then, will already have reached its quiet end. None of this is sad. A merger of galaxies is not a destruction, but a transformation. Two great spirals, each one built up over billions of years from countless mergers of its own, coming together slowly and becoming something new, something larger, something that will itself drift for billions of years in the expanding universe, orbited by the dimming remnants of 1 trillion stars. The universe does not destroy, it transforms. And on timescales like these, transformation and rest are the same thing. Change so slow it is indistinguishable from stillness. You are resting now in the middle of a story that stretches billions of years in both directions. The collision is coming in a time so far away it has no emotional weight at all. Just a fact, a quiet, extraordinary fact about the future of your galaxy. Let it rest lightly in your mind, something vast and distant and patient. The galaxy, as always, has time. We have traveled very far on this journey. We have drifted through the spiral arms and floated above the galactic center. We have sat quietly with ancient stars in the deep halo, visited islands of old light in the surrounding dark, passed through the cold chemistry of the interstellar medium, and watched the slow merger of a small galaxy with our own. We have journeyed outward to the satellite galaxies and forward in time to the distant collision with Andromeda. And now, gently, we come home. We come back to the surface of a small blue planet, orbiting an ordinary star in a quiet spur of a spiral arm. We come back to the night sky as it can be seen from the ground, with nothing but the naked human eye and a little darkness and a little patience. Because all of this, everything we have described, is also something that exists above your head on a clear, dark night. The Milky Way is not only a subject of scientific study, it is also something you can see, something our ancestors saw every night of their lives, something our bodies evolved beneath, something the human eye was shaped over millions of years of evolution to perceive. Let us spend this last section simply looking quietly together to see the Milky Way with the naked eye. You need two things above all others: dark skies and time. The Milky Way, as seen from Earth, appears as a broad, soft band of pale light stretching from horizon to horizon. Not a sharp line, not a bright stripe, just a gentle, slightly luminous thickening of the sky, a region where the stars are so numerous and so closely packed that they blur together into a continuous, diffuse glow. A river of pale light, softer than moonlight, stretching across the whole sky. But this sight is increasingly rare. Approximately 80% of people in the United States and about a third of the global population now live under skies so contaminated by artificial light that the Milky Way is completely invisible. The orange and white glow of cities scatters upward into the atmosphere, lighting the sky from below, drowning the faint glow of the galaxy in a permanent false twilight. Entire generations are growing up without ever seeing the river of light that their ancestors regarded as one of the most basic features of the night sky, the thing that prompted the Greeks to tell their story of spilled divine milk, the pathway of the birds that Finnish people navigated by, the road of the sand girls' scattered embers, all of it invisible now to most of the people alive on Earth. But it is still there. Drive far enough from any city, climb high enough into unpolluted mountains, cross into a desert or a wilderness far from human settlement, and on a clear, moonless night, the Milky Way will return. The experience of seeing it for the first time, or after a long absence, is difficult to describe. Most people, in their first moment of genuine dark sky clarity, feel something that is hard to separate from emotion, a sense of scale, of smallness, of deep, quiet belonging. The sky is suddenly not a ceiling, but a depth, not a dark backdrop, but a luminous, three-dimensional universe. What the eye sees under truly dark skies is this: a pale band of light, perhaps as wide as the span of a hand, held at arm's length, arching overhead, slightly brighter in some places than others, brightest in the direction of Sagittarius and Scorpius in the summer sky, where we are looking toward the galactic center. Through the densest concentration of stars in the disk, fainter and more diffuse in the winter sky, where we look outward toward the galaxy's edge. Along the band, there are dark regions too, patches where the glow seems dimmer, where the light of the stars behind them is blocked by the dust clouds of the interstellar medium. The Great Rift, as it is sometimes called, a dark lane running through the band from the constellation Cygnus all the way down to Sagittarius. The dark clouds of the coal sack near the Southern Cross, not absences of stars, but presence of dust, the same interstellar medium we drifted through earlier in this journey, now visible from the outside as a shadow through the galaxy's light. The darkest skies on Earth have a quality that cannot be photographed. Long exposure photographs of the Milky Way are extraordinarily beautiful. They reveal colors the human eye cannot see in real time. The deep red of hydrogen emission nebulae, the blue of reflected starlight in dust clouds, the subtle variations of star density that trace the spiral arms. These images are true. They show real features, but they are not what the eye sees. What the eye sees is more subtle and in some ways more profound. The Milky Way to the naked eye is pale, almost colorless, a soft luminescence rather than a blaze of color. The eye's color receptors, the cone cells, are not sensitive enough in low light to pick up the colors that the galaxy contains. What we see is detected mostly by the rod cells, the low light sensors of the retina, which register brightness but not color. So the Milky Way appears to us as a wash of silver and gray and pale white against the black of the sky. Ancient and honest and quiet, the way the human eye has always seen it. There is a practice among experienced stargazers called averted vision. The center of the human retina, the fovea, is packed with cone cells optimized for color and detail in bright light. But the periphery of the retina has a higher density of rod cells. The dim light detectors, when you look directly at a faint object, the light falls on the less sensitive central fovea. But when you look slightly to one side of it, the light falls on the more sensitive peripheral rods. The object appears slightly brighter, slightly more defined. Skilled observers use this technique constantly. To see faint nebulae, to resolve the outer stars of a globular cluster, to catch the first hint of a galaxy too faint for direct vision. Averted vision is the art of seeing by not quite looking, of finding something faint by directing your attention gently to one side of it and letting your peripheral sensitivity do the work. It is a gentle metaphor for for a kind of attention that goes beyond stargazing. Some things are perceived more clearly when you do not stare directly at them. When you let your attention soften and drift slightly to the side, when you stop trying so hard to see. The best time to see the Milky Way from the northern hemisphere is in summer, when the Earth's night side faces toward the galactic center in Sagittarius. From late June through September, on moonless nights, the core of the Milky Way rises in the south, dense and bright, and the band of the galaxy arches overhead like a slow, enormous river. From the southern hemisphere, the view is even more dramatic. The galactic center passes almost directly overhead in the winter months of the southern sky. From dark locations in Australia, New Zealand, southern Africa, the high deserts of Chile and Argentina, the Milky Way is not just visible, but overwhelming. It fills the sky from horizon to horizon with a complexity and brightness that leaves those who see it for the first time without adequate words. The large and small Magellanic Clouds, those two companion galaxies we visited earlier in this journey, are also visible from the southern hemisphere as soft patches of light near the south celestial pole, like detached pieces of the Milky Way drifting in the dark to other galaxies, visible with the naked eye, keeping quiet company with our own. There are designated places around the world called international dark sky sanctuaries and dark sky parks, places where light pollution has been controlled or is naturally absent. The Atacama Desert in Chile, Natural Bridge National Monument in Utah, Yoraki Mackenzie International Dark Sky Reserve in New Zealand, the island of Sark in the British Channel Islands, the first dark sky island in the world. These are places protected not for their minerals or their timber or their water, but for their darkness, for the simple, irreplaceable quality of a night sky undimmed by human light. In these places, people travel specifically to lie on their backs and look up, to do what human beings have done for 100,000 years or more, under every sky on every continent, to see the river of light, to feel small and connected and strangely comforted by the enormity above them. Here is what we know, having spent this long night in the galaxy together. The pale band of light visible from a dark field is not just a pretty feature of the night sky. It is the disk of our home galaxy, seen edge-on from the inside. The slightly brighter regions are the spiral arms, denser with stars. The dark lanes are the dust clouds of the interstellar medium. The brightest glow in the south is the galactic center, 26,000 light years away, where Sagittarius A sits dark and patient at the heart of everything. The individual stars scattered around the band are our stellar neighbors, the few dozen nearest suns of the local arm, and the faint, fuzzy smudge in Andromeda, if the sky is dark enough and you know where to look, is 2.5 million light years of distance, and the light of 1 trillion stars arriving gently in your eye after traveling longer than our species has existed. All of this is accessible to human eyes, directly, without any instrument, without any technology beyond the ancient, patient biology of a retina adapted to the dark. You were built to see this. And somewhere outside, right now, the Milky Way is turning. The ancient band of light is arching overhead, not waiting, not performing, just there as it has always been, patient and vast and quietly, breathtakingly present. As you have been on this long journey through the galaxy, present, quiet, breathing slowly, resting. Part of it, always part of it. The Milky Way does not exist in isolation. We have traveled through its spiral arms, its ancient halo, its satellite companions, and we have imagined its far future. But the galaxy itself is part of something larger, a small community of galaxies, bound together by gravity, drifting together through the cosmos, each one distinct and self-contained, and yet connected to the others by invisible threads of gravitational attraction. This community is called the local group, It is our galactic neighborhood, the collection of galaxies close enough to us to be gravitationally bound, close enough to influence each other's paths, close enough that we can study their individual stars and star clusters and gas clouds in detail impossible for more distant galaxies. The local group spans a volume approximately 10 million light-years across, a small neighborhood in cosmic terms, a modest gathering. The local group contains at least 134 known galaxies within its central regions, and the true number is likely higher, with faint dwarf members still being discovered in the outer reaches. Most of them are small. Most of them are dim. Most of them are dwarfs, ancient and sparse, orbiting the two great spirals that dominate the group like moons orbiting planets. Let us step back a little tonight. Let us look at the whole neighborhood, slowly, without hurry. If you could somehow rise far above the local group and look down at it from a great distance, what you would see would have a distinctive shape. Not a sphere, not a cluster, something more like a dumbbell. Two lobes of galaxies, each one centered on one of the two dominant spirals, separated by a relatively empty middle space and slowly falling toward each other. One lobe is centered on the Milky Way. All of the satellite galaxies we have discussed on this journey belong to this lobe. The Magellanic Clouds, the Sagittarius Dwarf, the classical dwarf spheroidals like Sculptor and Fornax and Carina, the ultra-faint dwarfs, barely detectable even with modern telescopes. 60 or more small companions, all orbiting the Milky Way in their long, looping paths. The other lobe is centered on Andromeda. The Andromeda galaxy has its own retinue of satellites, its own family of dwarf companions orbiting it the way ours orbit us. Among them are NGC 147, NGC 185, and NGC 205, small elliptical galaxies visible through a modest telescope, and the Triangulum galaxy M33 sits between the two lobes, its membership uncertain, perhaps a satellite of Andromeda, perhaps a more independent member drifting in the space between the two great spirals, between the two lobes, in the relative emptiness between our galaxy and Andromeda. There are almost no galaxies at all. Just 2.5 million light years of dark space, and the slow, inevitable gravity drawing the two lobes together. Let us spend a little time with the Triangulum galaxy. M33, as astronomers catalog it, is the third largest member of the local group. It contains roughly 50 billion stars spread across a disk about 60,000 light years wide, a smaller and less imposing galaxy than either the Milky Way or Andromeda, but a spiral galaxy in its own right. One of only 3 spiral galaxies in the local group. From a dark sky location in the northern hemisphere, on a very clear and very dark night, the Triangulum galaxy is just barely visible to the naked eye. It appears as the faintest possible smudge, almost too diffuse to be certain of. Experienced observers can detect it under ideal conditions, making it arguably the most distant object visible to the unaided human eye at approximately 2.7 million light years. But through binoculars or a small telescope under dark skies, M33 reveals itself. A soft, face-on spiral, its disk glowing faintly, its spiral arms just hinting at their shape, and within those arms, particularly bright and pink-tinged, is NGC 604, a giant star-forming region so large that if it were placed where the Orion Nebula sits, it would span more than a third of the sky and be bright enough to cast shadows on the ground at night. The most luminous emission nebula in the entire local group, containing hundreds of young, massive stars recently formed from its dense gas. A star nursery in a neighboring galaxy, visible in its broadest outlines through a backyard telescope on a good night. The local group is itself gravitationally bound to a larger structure. It sits within something called the local sheet, a flattened arrangement of galaxy groups spread across a region roughly 30 million light years in diameter, all moving together through space with a common drift, all participating in the expansion of the universe, but also bound loosely to each other by gravity. The local group, the 81 group, centered on the beautiful spiral 81 in Ursa Major. The sculptor group, a loose gathering of galaxies in the southern sky. The Centaurus A group and others, each one a small family of galaxies, each family part of the same broad neighborhood. And the local sheet is itself embedded in the Virgo supercluster, a vast structure centered on the Virgo cluster of galaxies, roughly 65 million light years away, containing more than 1,000 galaxies. The Virgo cluster is massive enough that its gravity slows our recession from it slightly, pulling the local group gently toward it against the expansion of the universe. In a motion astronomers call the Virgo infall, and even the Virgo supercluster, vast as it seems, is merely one lobe of the Laniakea supercluster, a structure whose name comes from the Hawaiian words for immeasurable heaven. 500 million light years across, containing the mass of 100 million billion suns, home to 100,000 galaxies. The Milky Way is one galaxy among those 100,000. These are the layers of home. The Milky Way, the local group, the local sheet, the Virgo supercluster, Laniakea, each one a larger embrace containing everything inside it, each one a community of a different kind, bound together by gravity at a different scale, participating in a different rhythm of motion and interaction. And beyond Laniakea, the observable universe contains roughly 2 trillion galaxies. 2 trillion. Each one a collection of hundreds of billions of stars. Each one a home to its own interstellar medium, its own dark matter halo, its own satellite companions, its own ancient halo stars, carrying the memory of its earliest formation. 2 trillion galaxies. And in the long future of the expanding universe, most of them are receding from us, moving further away, expansion of the universe is accelerating, driven by the mysterious dark energy that permeates all of space, pushing the fabric of the cosmos outward faster and faster. In the far future, only the galaxies of the local group will remain close enough to be reachable. Everything beyond it will have receded beyond the cosmic horizon. The rest of the universe, those 2 trillion other galaxies, will eventually become invisible, unreachable, as if they never existed. But the local group will remain. Our small family of galaxies, bound together by gravity, immune to the expansion, drawn toward each other while the rest of the universe withdraws. There is something very tender in that image. A small cluster of galaxies holding together in the dark while the larger universe expands away from them. The Milky Way and Andromeda, slowly approaching each other, destined to merge, the Triangulum galaxy drifting nearby, its great star-forming nebula still blazing with new suns. The Magellanic clouds trailing their slow river of gas. The ancient dwarf spheroidals following their long orbits through the halo, all of them part of the same small family, all of them bound together, all of them going nowhere in the cosmic sense, just drifting and orbiting and slowly merging in the small warm pocket of the universe that gravity has managed to hold together against the great outward expansion of everything else. Our local group is a refuge, an island of bound structure in an accelerating cosmos. It is the neighborhood we will always have, long after the last distant galaxies have receded beyond sight, long after the universe has grown cold and dark beyond our small, gravitationally bound family. The local group, or whatever it has become by then, will still be here, merged and transformed, but here, right now, all of this surrounds you. The satellite galaxies drift in their slow orbits above and below the disk. The Andromeda galaxy hangs in the autumn sky, 2.5 million light years away. A faint smudge carrying the light of 1 trillion stars. The Triangulum galaxy drifts nearby, barely barely visible, its great nebula blazing within its spiral arms. And further out, the other galaxies of the local group drift in the dark, all of them part of the same gravitationally bound family, all of them participating in the same slow story. You are not alone in the universe. You are part of a family, layer upon layer of families, each one held together by the same patient force that holds your body gently to the earth. Gravity binds the galaxy. Gravity binds the local group. Gravity holds the supercluster together. And right now, quietly and without effort, it holds you too. Rest in that. Let the neighborhood expand gently in your imagination. Galaxy after galaxy, each one a home, each one ancient and vast, all of them yours in the simplest possible sense. You are part of the same universe as all of them. The same laws, the same constants, the same patient, irresistible pull of matter toward matter. You are home. You have always been home. Everything we have described on this long journey through the Milky Way is the result of a process, not a single event, not a moment of creation in which the galaxy appeared, fully formed, with its spiral arms and its central bar and its ancient halo and its 150 globular clusters all in place, but a process, a slow, patient, 13 billion year process of gathering and merging and forming and scattering and forming again, of matter finding matter, of gravity drawing things together, of the galaxy building itself, one star and one merger, and one slow revolution at a time. Tonight, in this final stretch of our journey, let us trace that process. Let us begin at the very beginning, when there was no galaxy here at all. And let us walk forward through time slowly, the way the galaxy itself moved forward through time, without rushing, pausing at each great chapter, letting the long sweep of it settle gently in the mind. 13.8 billion years ago, the universe began. In the first moments, there were no stars, no galaxies, no planets, heavier than hydrogen and helium, and a trace of lithium. Just an extraordinarily hot, dense, rapidly expanding sea of energy and matter, cooling as it expanded, thinning as it spread outward in all directions. For the first few 100 million years, the universe was dark. Astronomers call this period the cosmic dark ages. The universe had cooled enough that matter and energy had separated. Neutral hydrogen gas filled all of space, cool and dark, and essentially featureless. No stars burned, no light traveled freely through the fog. Just the slow, gradual thickening of slightly denser regions of gas, where the tiny quantum fluctuations of the universe's very first moments had left their fingerprints, regions a fraction denser than their surroundings. And gravity, patient as always, slowly amplifying those tiny differences, drawing the denser regions in on themselves, building very slowly the seeds of the first structures. The dark matter was doing most of the structural work. Dark matter, insensitive to the pressure forces that slowed the ordinary gas from collapsing, began to form the first halos. Great, roughly spherical knots of invisible mass, gathering at the intersections of the cosmic web of dark matter filaments that threaded through all of space and ordinary matter, hydrogen and helium, fell into these dark matter halos under gravity, pooled within them, began to cool, began to condense. Approximately 100 to 200 million years after the Big Bang, the first stars ignited. These first stars, called population III stars by astronomers, were unlike any stars that exist in the galaxy today. They formed from gas that was almost entirely hydrogen and helium, containing none of the heavier elements that later generations of stars would produce. Without heavier elements to help cool the collapsing gas, the first stars were enormous, hundreds or even thousands of times the mass of our sun. They burned brilliantly and very briefly, living perhaps 1 million years before exploding as supernovae of extraordinary violence. And in those explosions, they did something of permanent importance. They scattered the first heavy elements into the surrounding gas. The first carbon, the first oxygen, the first iron. Small amounts, tiny traces, but present now in the gas of the young universe for the first time. The first enrichment, the universe's first step toward complexity. These first massive stars also flooded the surrounding gas with ultraviolet radiation, ionizing the neutral hydrogen that had filled space since the cosmic dark ages. This process, called reionization, gradually cleared the cosmic fog, making the universe transparent to light in a way it had not been since the very earliest moments after the Big Bang. In the densest regions of the young universe, where dark matter halos were large enough and the gas was dense enough, the first small galaxies began to form. Not galaxies like the Milky Way, not great spirals with spiral arms and bars and bulges, just small, irregular clumps of gas and young stars, proto-galactic fragments, the first gathering of matter large enough to be called, in any meaningful sense, a galaxy. And these small fragments began to merge. The early universe was far more densely populated with small galaxies than the universe today. The distances between things were smaller. Mergers were frequent. And through these repeated mergers, small fragments combined into larger structures. The larger structures merged in turn. The Milky Way, in its earliest form, was one of these growing structures, not yet a spiral, not yet a disk, just a messy, irregular, actively merging concentration of gas and young stars, gradually growing by absorbing everything around it. About 13 billion years ago, a disk began to form. Research published in 2022, using data from the Gaia satellite and analysis of nearly 250,000 stars, found evidence that the Milky Way's thick disk began forming approximately 13 billion years ago, just 800 million years after the Big Bang itself. Earlier than most astronomers had expected. The galaxy was already beginning to organize itself, already developing the flat, rotating disk structure we recognize today. Astonishingly early in cosmic history. The thick disk of the Milky Way, that older, more diffuse layer of stars above and below the thin disk, is a relic of this early epoch. Its stars, many of them 10 to 13 billion years old, still orbit today in their slightly tilted, slightly more energetic paths, living memories of the galaxy's turbulent teenage years. Then, approximately 11 billion years ago, something dramatic happened. A large dwarf galaxy collided with the young Milky Way. This ancient galaxy, discovered through its traces in the Gaia data and named Gaia Enceladus, was a substantial object, estimated to have contained perhaps 500 million to several billion solar masses of stars. It was the most significant merger in the Milky Way's entire history, larger and more violent than anything that has happened to our galaxy since. The collision was not gentle. The stars of Gaia Enceladus were flung into chaotic, highly elliptical orbits that still populate the Milky Way's inner halo today, when astronomers measure the velocities and chemical compositions of halo stars. They can still identify the blue, metal-poor stars of Gaia Enceladus, moving on their ancient, disrupted paths, distinguishable from the native Milky Way stars, even 11 billion years after the collision. The impact also triggered an extraordinary burst of star formation. The collision compressed gas across the young Milky Way, collapsing molecular clouds and igniting new stars at a rate the galaxy has never matched before or since. The star formation rate peaked around 11 billion years ago, fueled by the gas of both the Milky Way and its ancient intruder. Hundreds of millions of new stars born in the turbulence of that great encounter. Many of them are still with us, still burning, still tracing the orbits they were born into 11 billion years ago. Over the next several billion years, the galaxy settled. The violence of the Gaia-Enceladus merger gradually faded as the disrupted material dispersed into the halo, and the remaining gas settled into increasingly organized rotation. The thick disk, still forming stars from its supply of gas, slowly enriched itself with heavier elements as successive generations of massive stars lived and died within it. The stellar populations of the thick disk show this enrichment clearly. The oldest thick disk stars are metal poor. The younger ones contain progressively more of the heavy elements forged by the generations before them. The history of enrichment, written in the chemistry of billions of individual stars. Approximately 8 billion years ago, the thick disk ran out of gas and stopped forming stars. Fresh gas in the outer regions of the galaxy, no longer consumed by the vigorous star formation of the thick disk era, began to settle inward, cooling, flattening, forming the thin disk. The galaxy's second great chapter of star formation began. Quieter, more organized, the thin disk building itself up over the subsequent 8 billion years, star by star, spiral arm by spiral arm, gradually becoming the disk we live in today. Our sun formed 4.6 billion years ago. Halfway through the thin disk's history, in a molecular cloud enriched by 8 billion years of previous stellar generations, made of gas containing the carbon and oxygen and iron and silicon produced by all the stars that lived and died before it. A third generation star, perhaps, or fourth, built from the recycled remains of many previous suns. By the time the sun formed, the Milky Way was already ancient, already more than 9 billion years old, already carrying within it the halo stars of Gaia-Enceladus, still orbiting in their disrupted paths, already home to hundreds of billions of stars, already shaped broadly as it is today. Our solar system was born late into an old galaxy, a galaxy that had already been building and merging and forming for longer than the current age of our solar system. We are, in a very real sense, latecomers And yet we arrived in time to find the galaxy at the height of its settled, organized, thin disk maturity. A quiet, stable epoch, the Milky Way's long afternoon. 13 billion years of becoming. Dark matter halos gathering in the cosmic dawn. The first enormous stars igniting and dying. Small proto-galactic fragments merging into larger structures. The turbulent collision with Gaia Enceladus and the great burst of star formation it triggered, the thick disk forming and enriching and quieting. The thin disk settling into its flat, organized rotation. The spiral arms winding, the bar taking shape, the globular clusters forming early and drifting into their long halo orbits, and finally, deep in the thin disk's long settled maturity, a small star forming in a quiet spur of a spiral arm, and around that star in time, a small blue world, and on that world in time, life that learned to look up. You are the latest chapter of a 13 billion year story. Not the last chapter. Not even close to the last chapter, but one of the most recent. A moment in the long middle of the galaxy's ongoing life, when the conditions happened to be right for something like you to exist, and to rest, and to listen to quiet words about the place you came from. Let that settle in like something warm and ancient. You are not separate from the galaxy's history. You are made of it, assembled from its recycled material, carried in its orbit, living in its long, quiet afternoon. 13 billion years of the universe becoming, so that tonight this could happen. We have traveled far on this journey, from the ancient stories of people lying in the dark, looking up at a river of light, through the spiral arms and the galactic center and the deep surrounding halo, through the birth and death of stars, through the long 13 billion year history of our galaxy's slow becoming. Now let us travel forward, not just a few billion years, to the collision with Andromeda. Further than that, much further, into a future so vast that the numbers involved lose any ordinary meaning and become something more like poetry, a future in which the stars themselves grow old and quiet, one by one, until the last light in the galaxy fades and something new and unimaginably patient begins. This is not a dark story. It is the story of an extraordinary patience, of things enduring for lengths of time that make our entire cosmic history, from the Big Bang to tonight, seem like the briefest of opening moments. It is the story of the universe doing what it always does, changing slowly, without hurry, following the laws of physics to their most remote and gentle conclusions. Let us drift into it now, slowly as the stars themselves will dim. We live in what astronomers call the stelliferous era, the era of stars. It began roughly 100 million years after the Big Bang, when the first stars ignited. And it will last for approximately 100 trillion years. 100 trillion. We are currently about 13.8 billion years into the stelliferous era. Barely 1/10,000th of the way through it. The era of stars is overwhelmingly, staggeringly young. We are in the very opening pages of the age of stars, not approaching its end. For most of the stelliferous era, the universe will continue to look broadly as it does now. Galaxies of stars drifting through the expanding cosmos. New stars forming from gas clouds, old stars dying and scattering their material back into the interstellar medium. Planetary systems, nebulae, all the structure and activity we have described on this journey, continuing for timescales we cannot meaningfully compare to anything in human experience. But slowly, the era will wind down. The supply of fresh gas available for star formation is finite. With each generation of stars, some fraction of the galaxy's gas is locked away in stellar remnants. White dwarfs, neutron stars, black holes, material that will never again participate in star formation. Over hundreds of billions of years, this slow locking away of material will exhaust the gas reserves of the galaxy. Star formation will not stop suddenly. It will simply diminish gradually, star by star, cloud by cloud. The rate of new star formation will fall. The galaxy will grow quieter. The most massive stars, which burn through their fuel in only a few million years, will be the first to go. Their brief, brilliant generation will end relatively soon. The blue giants of the spiral arms will fade. Then the sun-like stars will exhaust their fuel over billions of years, swelling into red giants, shedding their outer layers as planetary nebulae, leaving behind white dwarfs. And then, long after all of that, the red dwarfs will remain. The last stars burning in the Milky Way will be red dwarfs. Those small, dim, extraordinarily long-lived stars that make up 3/4 of all the stars in the galaxy today. Stars that burn so slowly and so efficiently that they can sustain fusion for tens or even hundreds of trillions of years in a galaxy that will grow progressively dimmer and quieter as its larger stars die. The red dwarfs will persist long after our sun has become a white dwarf, long after the last blue giant has exploded, long after the last sun-like star has shed its planetary nebula into the interstellar medium. The red dwarfs will still be burning, small and cool and dim and patient. The last red dwarf star to exhaust its fuel will do so approximately 100 trillion years from now. At that moment, the stelliferous era ends. The last fusion-powered star in the galaxy flickers and goes out. And for the first time in 100 trillion years, no new light is being generated anywhere in what was once the Milky Way. The era of stars is over. What follows is called the degenerate era. The universe does not become empty. It becomes a landscape of remnants. White dwarfs, the cooling cores of stars like our sun, will dominate. There will be an extraordinary number of them. Every star between roughly 8/10 and 8 times the mass of the sun ends its life as a white dwarf. Given that the vast majority of stars in the galaxy galaxy fall within this range. The Milky Way, or what remains of it after its mergers and transformations, will be populated by hundreds of billions of white dwarfs, each one roughly the size of the Earth, each one made of carbon and oxygen, crystalline and dense, slowly, very slowly, cooling. They will cool for an almost unimaginable length of time. A white dwarf radiates its heat into space the way a brick radiates the warmth of an oven. Slowly, steadily, without any internal heat source to replenish it. The cooling rate depends on the mass and composition of the white dwarf, but even the fastest cooling white dwarfs will take hundreds of billions of years to approach the temperature of their surroundings. And as the universe itself grows colder, approaching the temperature of the cosmic background, the white dwarfs will cool along with it. After perhaps 10 trillion to 100 trillion years, the coolest, oldest white dwarfs will have cooled so completely that they no longer glow visibly. They will have become black dwarfs, cold, dark, solid spheres of crystallized carbon and oxygen, roughly the size of the Earth, drifting invisibly through the dark remnants of the galaxy. No light, no warmth, not even the faint infrared glow that a cooling white dwarf emits. Just cold, dark, crystalline mass drifting in the dark. Not a single black dwarf exists anywhere in the universe today. The universe is not old enough. Every white dwarf that has ever formed is still warm, still fading. The first black dwarfs will not appear for trillions of years yet. We are far too early in the universe's story to have witnessed the death of even one white dwarf. But even in the degenerate era, the universe will not be entirely without events. Occasionally, over vast stretches of time, two white dwarfs in a binary system will spiral toward each other, losing orbital energy to gravitational radiation until they collide and merge. If their combined mass exceeds a certain threshold, the collision can reignite nuclear fusion, briefly, in a flash of stellar light. A single brilliant event, fading over weeks, in an otherwise dark sky. And there are even stranger possibilities. A physicist named Matthew Kaplan published a remarkable paper in 2020 proposing that in the very far future, somewhere between 10 to the 1,000 and 10 to the 10,000 years from now, a number so large it cannot meaningfully be written out, the slowest possible nuclear reactions within black dwarfs will have gradually processed their interiors toward iron, the most stable configuration of matter. And when enough iron has accumulated in the core of a black dwarf, the core will collapse, and the black dwarf, cold and dark and silent for quadrillions of years, will briefly explode. A supernova from a dead star. No one will be there to see it. It will happen in a universe so cold and dark and vast that the concept of observation will have lost all ordinary meaning. But it will happen, the laws of physics, patient beyond any human conception of patience, will eventually carry even the cold, dead remnants of stars to their final transformation. Further still, in the black hole era, the white dwarfs and neutron stars will have decayed. Only black holes will remain as significant concentrations of mass. The supermassive black holes at the centers of merged galaxies. The stellar mass black holes scattered through the dark, all of them slowly, almost imperceptibly, evaporating via a quantum process called Hawking radiation, leaking energy one quantum at a time into the surrounding space. The larger the black hole, the more slowly it evaporates. A supermassive black hole will take perhaps 10 to the 100 years to fully evaporate. And when the last black hole is gone, the dark era begins. A universe containing nothing but a thin, cold, diffuse gas of photons and electrons and positrons and neutrinos, expanding forever, cooling forever, growing more dilute with every passing moment. No structures, no concentrations, no events worth naming, just the slow expansion of a universe that has used up everything it had. And yet, even now, resting here in this particular moment in the stelliferous era. We exist in the most luminous, most active, most structurally rich epoch the universe will ever know. The stars are burning, the gas clouds are forming new suns, the galaxies are turning. The interstellar medium is cycling its material through generation after generation of stellar lives. The Milky Way is at the height of its settled, thin disk maturity, orbited by its companions, carrying its ancient halo stars, sheltering its small blue planet. This is the golden age of the universe, and we are in it. 100 trillion years of the stelliferous era remain ahead of us, and we exist here, near the beginning of it, while the stars still burn in their billions, while the spiral arms still glow, while the night sky still carries the river of light that ancient people looked up at and named with their best words. The long, slow dimming is coming, but it is very, very far away. And tonight, the stars are bright. Let that be a comfort, a deep, quiet, unhurried comfort. The universe has given us the brightest moment of its long life, and you are resting in it, warm and still, on a small blue world orbiting one of those billions of burning stars in the galaxy's long, golden, luminous afternoon. The stars burn on, for now and for a very long time yet. The stars burn on. One of the most curious things about living inside a spiral galaxy is that we cannot see our own home from the outside. We cannot step back far enough. We cannot rise above the disk and look down at the shape of our own galaxy, the way you might look at a city from an airplane window, seeing its layout and its pattern and its full extent all at once. We are inside it. We have always been inside it. And so, we must piece together the shape of our home from incomplete information, from measurements taken within the galaxy itself, from the motions of stars and the distances to gas clouds and the careful interpretation of data gathered over decades. But the universe, generous as it is, has given us something else. it has given us other spiral galaxies. Out there in the dark, at distances of millions of light years, there are spiral galaxies we can see whole. Galaxies we can observe from outside, their structures fully revealed, their arms and bars and bulges displayed to us with a clarity our own galaxy can never offer. And in studying them, we study ourselves. We see in those distant spirals what the Milky Way must look like to an imagined observer in some other galaxy, looking across the dark in our direction. Let us visit some of these mirrors tonight, slowly, each one a galaxy entire, each one a home to hundreds of billions of stars, each one turning patiently in the dark. The first spiral galaxy ever identified as such was the Whirlpool Galaxy. Its catalog name is Messier 51 or M51. It lies approximately 31 million light years from Earth in the constellation Canes Venetis, the hunting dogs, a faint constellation just below the handle of the Big Dipper. On a very dark, clear night, it is just barely detectable through binoculars as a faint smudge. Through a modest telescope, something more remarkable appears. Two objects close together, one larger and brighter, one smaller, slightly dimmer, appearing almost to touch. The larger is the Whirlpool Galaxy itself. The smaller is its companion, NGC 5195, a dwarf irregular galaxy that has been interacting with M51 for hundreds of millions of years. It may have passed directly through the disk of M51 500 to 600 million years ago, and again as recently as 50 to 100 million years ago, and that interaction has shaped the whirlpool into one of the most striking spiral galaxies in the sky. The gravitational disturbance of NGC 5195 passing through M51's disk has enhanced and reinforced its spiral arms, compressing the gas along them and triggering waves of star formation. The result is what astronomers call a grand design spiral. Not a flocculent spiral with patchy, irregular arms, but a true, sweeping, two-armed spiral with long, graceful, continuous arms that wind around the galaxy like the curves of a seashell. The whirlpool's spiral arms glow with the blue light of newly formed massive stars, lit from within by the same process we described in the star nursery sections of this journey. Star-forming regions strung along the arms like beads on a curve. The galaxy's beauty is not decorative. It is functional. The arms are the galaxy's way of making new suns. At the heart of the whirlpool galaxy, there is an active galactic nucleus, a central black hole more active than our own Sagittarius A, surrounded by a disk of hot gas, producing a faint but detectable glow of X-ray radiation. The sleeping giant at the center of the whirlpool is not entirely asleep. Now let us turn northward in the sky to one of the largest and most face-on spiral galaxies visible from Earth, the Pinwheel Galaxy, Messier 101. It lies approximately 21 million light-years away in the constellation Ursa Major, the Great Bear, the same constellation that contains the familiar stars of the Big Dipper. On the clearest, darkest nights, it is just detectable to the naked eye as an extremely faint, diffuse glow. Through a telescope, it reveals itself slowly, a large, face-on spiral, dimmer and more spread out than its smaller apparent companions in the sky, but magnificent in its breadth. The Pinwheel Galaxy is nearly twice the diameter of the Milky Way. Its disk stretches approximately 170,000 light-years across, containing at least 1 trillion stars. What is striking about Moan 101 is its asymmetry. Unlike the whirlpool with its two balanced grand arms, the pinwheel is lopsided. Its spiral arms are unevenly developed. One side of the galaxy is more richly populated with star-forming regions than the other. Giant HII regions, vast glowing clouds of ionized hydrogen lit by massive young stars, are distributed asymmetrically around the disk, concentrated in some arms and almost absent from others. This asymmetry is thought to be the result of gravitational interactions with companion galaxies. The pinwheel has several smaller companions, and their tugs and pulls over billions of years have distorted the galaxy's disk, creating the uneven distribution we see today. The pinwheel is a reminder that no galaxy exists in isolation. Every spiral carries the signatures of its history written in the distribution of its light. Let us visit one more galaxy tonight, one of the most unusual and beautiful objects in the night sky, the Sombrero Galaxy, Messier 104. It lies approximately 29 million light years from Earth in the direction of the constellation Virgo. Through a telescope, it presents a breathtaking edge-on view. A bright, oval central bulge, unusually large compared to the disk, glowing with the warm amber light of billions of old stars, and encircling that bulge, running around its equator like the brim of a hat, a thick, dark lane of dust. The dust lane of the interstellar medium, seen edge-on, absorbing the light of the stars behind it, creating a dark band that gives the galaxy its name. The Sombrero. It is a beautiful name for a beautiful object, and the shape is striking precisely because we can see both the disk and the bulge in clear contrast. The disk is thin, the bulge is enormous, the dust lane is thick and rich. The Sombrero Galaxy is somewhat unusual in having such a large central bulge relative to its disk. This proportion suggests it may be transitioning very slowly and over billions of years from a spiral toward something more like a lenticular or even an elliptical galaxy, a spiral in the process of settling, still carrying its disk and its dust lane, but dominated by its ancient, rounded core of old stars. At the heart of the Sombrero, there is a supermassive black hole, estimated to be about 1 billion times the mass of our Sun. Far larger and far more massive than Sagittarius A, one of the most massive black holes known in any galaxy of its size. It sits there, At the center of that enormous amber bulge, dark and patient and extraordinary, while the disk turns slowly around it. The dust lane that gives the galaxy its hat-brim shape is rich with gas and hydrogen, and within it, star formation continues. New suns being born in the shadow of a billion solar mass black hole in the dust lane of a galaxy that is slowly growing quieter. Each of these galaxies, the whirlpool, the pinwheel, the sombrero, is a complete world, a system containing hundreds of billions of stars, each with its own planets, its own interstellar medium, its own dark matter halo, its own ancient halo stars, its own central black hole, its own history of mergers and accretion, its own particular balance of star formation and stellar death, its own spiral arms or dust lanes or asymmetric distributions of light. No two spiral galaxies are identical. Each one is shaped by its particular history, its particular companions, its particular pattern of mergers and close encounters. The Milky Way from outside would be one more unique configuration in that great catalog of spirals. Our particular bar and our particular four-armed structure and our particular position of the sun in the Orion spur and our particular Sagittarius stream wrapping around our halo, distinctive, recognizable ours. And this is what the other spiral galaxies give us, above all else. Perspective. When you look at the whirlpool galaxy through a telescope, you are seeing something that took the light 31 million years to reach you. You are seeing a galaxy containing hundreds of billions of stars, each one a sun, most of them with planets. Some of those planets perhaps harboring conditions not entirely unlike the ones we know, all of it compressed into a small, faint, magnificent smudge in the eyepiece of a telescope. All of it present in the sky tonight, if the sky is dark enough and you know where to look. And our own Milky Way, the one you live inside, is just another galaxy in someone else's sky. Another faint, luminous smudge. Another spiral turning in the dark. carrying its 100 billion stars, carrying its one particular ordinary yellow star, and its one particular small blue planet, and everything on it. Everything on one small blue planet in one unremarkable spiral galaxy, 1 of 2 trillion in the observable universe. And yet here, on this particular planet, in this particular galaxy, something looked up, something noticed, something wondered, something lay in the dark and listened to quiet words about the place it came from. That is not ordinary. Whatever else the universe contains, that is not ordinary at all. Rest with that. Let the spirals turn in your imagination. The whirlpool and the pinwheel and the sombrero. And somewhere among them, too far away to see, the Milky Way, turning, carrying you, quietly and without any effort at all. We have come a very long way tonight. We began in the dark, with ancient people lying on their backs in the grass, looking up at a river of light they could not explain, and telling each other stories. Stories of spilled milk and stolen straw, and the pathway of birds flying south. Stories of a goddess stretching her body across the sky. Stories of a girl throwing embers into the dark so she would not be alone. And then we traveled inward into the shape of the great spiral disk, into the quiet neighborhood of our sun, settled in its modest spur between the arms. We wound through the spiral arms themselves, those slow density waves alive with new stars and glowing gas. We passed through the ancient central bar, warm and amber, and turning on its billions of years-long clock. We visited the heart of the galaxy, the roiling, dense, extraordinary central molecular zone with its exotic chemistry and its massive, short-lived stars. And at the very center of everything, we sat quietly with Sagittarius A, the sleeping giant, patient and dark, and 4 million times the mass of our sun, holding the entire galaxy in its slow gravitational embrace. We drifted out through the stellar halo, past the ancient metal poor stars still drifting faithfully in their long looping orbits after 13 billion years. We visited the globular clusters, those islands of old light, ancient and settled and serene. We let the invisible embrace of dark matter hold us. We breathed in the chemistry of the interstellar medium, drifting between the stars. We watched new suns being born in cold, dark clouds, and followed the full arc of a stellar life from its first ignition to its quiet, cooling end. We met the companions of the Milky Way, the Magellanic clouds bright in the southern sky, the Sagittarius Dwarf threading slowly through our disk, and we stepped back further to the local group, our small family of gravitationally bound galaxies drifting together through the expanding cosmos, holding together while the rest of the universe slowly withdraws. We rode the solar system's great galactic orbit, carried at 800,000 kilometers per hour, while feeling perfectly still. We imagined the slow approach of Andromeda and the distant transformation of two great spirals into something new. We walked the long 13 billion year history of our galaxy's patient becoming. From the first dark matter halos to the thin disk's golden afternoon. And we traveled forward into the far future, through the slow dimming of the stars, into the long, patient dark at the end of the stelliferous era, and found, even there, something restful and right. This has been a long night in the galaxy, and through all of it, you have rested. Let the words drift through you, the way starlight drifts through the interstellar medium, not holding on, not grasping, just receiving gently whatever arrived, and letting the rest pass by. If you are still awake, let your eyes stay closed. Let the images settle softly into the quiet part of the mind where things are kept not as facts, but as feelings, as a sense of scale, of connection, of home. You live in a barred spiral galaxy, 100,000 light years across, containing hundreds of billions of stars, orbited by ancient companions, wrapped in an invisible embrace of dark matter, turning slowly in the dark at the edge of the local group. In the early golden hours of the stelliferous era, in a universe has been building and breathing and becoming for nearly 14 billion years. And tonight, in the middle of all of that, you rested. You were still. You were warm. You were carried effortlessly through the dark on a pale blue world, orbiting an ordinary star in a quiet corner of a very beautiful galaxy. That is enough. That has always been enough. Sleep well. This has been Sleepy Facts with Justin. Thank you for traveling through the Milky Way with us tonight. The galaxy will still be here when you wake. Patient and vast and turning as it always has been, as it always will be. Good night.